At the heart of everything that makes up our universe, from the stars above to the very matter that forms us, lies an essential mystery: the origin of atoms. These incredibly tiny particles are the fundamental building blocks of all matter. They are the core of every solid, liquid, and gas, shaping everything we see, touch, and experience. But what about the atoms themselves? How did they come into existence? And could the entire universe, in some profound way, be likened to one vast, complex atom? This question invites us to explore one of the most mind-bending events in the history of science: the birth of the universe. A journey that takes us back to the very beginning, to a time before time itself, when the cosmos emerged from what we now call the Big Bang. The Big Bang, often described as the singular event that set everything into motion, is one of the most crucial concepts in modern science. It explains how the universe, in all its vast complexity, began. Picture, if you will, a time about 13.8 billion years ago, when the entirety of everything we know, every planet, every star, and even the space between them, was compressed into an unbelievably dense and hot point. This point, tiny beyond comprehension, held all the energy and matter that would later unfold into the galaxies, stars, and atoms we are familiar with today. In an instant, this dense, fiery point began to expand at a rate faster than the speed of light itself. This rapid expansion, known as inflation, wasn't an explosion in the traditional sense. Instead of debris flying outward, it was as if the very fabric of space-time itself stretched, carrying everything along with it. This moment marked the birth of not just the universe, but also the concept of time itself. There was no before the Big Bang, because time itself began with it. As the universe expanded, it remained extraordinarily hot. For a long time, atoms could not form. There simply wasn't enough room or stability for them. Instead, the early universe was a seething, glowing soup of subatomic particles, protons, neutrons, and electrons, all racing around at incredible speeds. But as the universe continued to cool and expand, these particles began to slow down, and eventually they came together to form the first simple atoms, primarily hydrogen and helium. These initial atoms, however, were not just isolated entities. Gravity, the unseen force that shapes the cosmos, began to pull these atoms together. Over time, clumps of gas grew dense and hot enough to trigger nuclear fusion, creating the first stars. These stars, massive and incredibly bright, became the heart of what would later grow into galaxies, vast collections of stars, gas, and dust, each group bound together by gravity and stretching outward across the universe like islands scattered on an endless ocean. And the story doesn't stop there. The universe, still expanding to this very day, is a dynamic place, constantly evolving. In the 1920s, astronomers discovered that galaxies are moving away from one another, a surprising and profound realization. The further away a galaxy is, the faster it appears to be moving. This observation suggests that space itself is still stretching, much like a balloon being inflated, carrying galaxies with it. The universe's expansion, once thought to have slowed down, is now believed to be accelerating, driven by mysterious forces that we have yet to fully understand. This discovery of an expanding universe raises fascinating questions. Will it continue to expand forever, eventually growing colder and emptier as stars burn out? Or could the universe reverse course, slowing down and collapsing in on itself in a dramatic event known as the Big Crunch? Or perhaps even more strangely, will the universe eventually rip apart in a big rip, where everything, stars, planets, even atoms, are torn apart as the expansion accelerates beyond our ability to comprehend? While we cannot yet answer these questions definitively, one thing is clear. The Big Bang did not just set the universe in motion, it created the very conditions for life itself. The elements forged in the hearts of the earliest stars became the building blocks for everything we know, from planets to the life that exists on them. The evidence for this grand tale is all around us. We detect the faint glow of radiation that lingers from the early moments of the universe, what we call the cosmic microwave background radiation. This ancient light, which has traveled across the universe for billions of years, offers us a snapshot of the cosmos when it was only about 380,000 years old, providing a glimpse into the universe's earliest days. As the universe cooled, stars and galaxies began to form, and these stars, in their fiery cores, created heavier elements like carbon, oxygen, and iron. These elements were then scattered throughout space in massive explosions known as supernovae, enriching the universe with the raw materials necessary for the formation of planets, and ultimately, life. Without these explosions, there would be no Earth, no stars like our Sun, and no possibility for life to take hold. However, the universe is not just expanding, it is evolving. The very structure of the cosmos is constantly being shaped by the interactions between galaxies, the birth and death of stars, and the mysterious forces at play behind the scenes. These forces, dark matter and dark energy, make up a vast majority of the universe's mass and energy, yet they remain invisible to us, detectable only by their gravitational effects. Dark matter is thought to be responsible for the way galaxies rotate, while dark energy is believed to be the driving force behind the accelerating expansion of the universe. The sheer scale of the universe is almost beyond our ability to comprehend. The Milky Way galaxy, our home, is more than 100,000 light years across, which travels at a staggering speed of 186,000 miles per second, would take over 100,000 years to cross the entire galaxy. And yet, despite this immense size, the universe is constantly growing, its galaxies moving further apart. In the grand scheme of things, our understanding of the universe is still in its infancy. While we have uncovered much about how it came to be, how it continues to evolve, and how atoms came to form the building blocks of everything, we are still only scratching the surface of what lies ahead. From the Big Bang to the creation of stars, galaxies, and the very atoms that make up our world, the universe is a living, breathing entity, ever expanding, ever changing. Its future, like its past, remains one of the greatest mysteries yet to be solved. And as we continue to peer into the depths of space and time, one thing remains certain. The Big Bang not only gave birth to the universe, but also set the stage for the incredible complexity that followed, from atoms to stars to life itself. What began as a single point in the fabric of space-time has unfolded into a vast and dynamic cosmos, an awe-inspiring story of creation, transformation, and exploration. The journey of the universe is far from over, and as we continue to look toward the stars, we may one day discover the ultimate fate of this cosmic tale. However, if a sufficiently large fluctuation were to occur, it could potentially trigger an event of unimaginable magnitude, akin to the Big Bang, a burst of energy so vast and powerful that it would rapidly expand into what we now call the universe. This profound event, which set the cosmos in motion, may have emerged from a quantum fluctuation, a brief moment of disorder within what was otherwise an empty vacuum. In the earliest moments following the universe's birth, it was far from the vast expanse filled with stars, planets, and galaxies that we recognize today. Instead, it was a chaotic, storm-like sea of energy, an unimaginable hot plasma where particles collided at mind-boggling speeds. At this stage, temperatures were so extraordinarily high that even the simplest atomic structures were unable to form. Particles constantly smashed into each other, broken apart in violent collisions, only to reform and collide again. But as the universe continued to expand, it gradually began to cool, and with this cooling came the possibility for something truly remarkable: the birth of atoms. The cooling of the universe allowed energy to transform into matter, a process governed by Einstein's famous equation, E equals mc squared, which asserts that energy and matter are interchangeable. As the energy levels dropped, subatomic particles, protons, neutrons, and electrons, began to take form. Protons and neutrons, bound by the strong nuclear force, came together to form the first clumps of matter. Electrons, far lighter than protons and neutrons, remained separate at first, zipping through the early universe in their chaotic dance. But the universe was still far too hot for these particles to form stable atoms. The intense energy kept shattering anything that tried to bond together. Approximately 3 minutes after the Big Bang, the universe had cooled enough for nucleosynthesis to begin. This process allowed protons and neutrons to merge and form the first atomic nuclei. Hydrogen and helium, the two simplest and most abundant elements, were the first atoms to take shape. Hydrogen, consisting of a single proton and a single electron, was by far the most abundant, while helium, made up of 2 protons and 2 neutrons, was the second most common. A small trace of lithium also formed at this stage. However, these nuclei were not yet stable atoms. The universe remained too energetic, and free electrons were continuously scattered by high-energy radiation, preventing atoms from fully stabilizing. It wasn't until 380,000 years after the Big Bang that the universe cooled enough for atoms to finally come into existence in their true form. This era, known as the era of recombination, marked a significant turning point in cosmic history. For the first time, electrons were able to settle into stable orbits around atomic nuclei without being constantly dislodged by high-energy photons, or particles of light. This allowed hydrogen and helium atoms to form in large numbers. With the advent of stable atoms, something extraordinary occurred. The universe became transparent. Before recombination, the universe had been a dense, foggy soup of free electrons and atomic nuclei, a scattering medium that kept light from traveling freely. But once the electrons bonded with the nuclei to form stable atoms, light was able to travel unimpeded through space. This cosmic radiation, released at the moment of recombination, is still visible today as the cosmic microwave background, CMB, a faint, omnipresent glow that scientists can detect from every direction. The CMB provides a window into the universe's infancy, allowing us to glimpse the conditions that existed when the cosmos was just a few 100,000 years old. Even though the first atoms had formed, the universe remained largely empty, dark, and cold, primarily filled with hydrogen and helium gas. However, gravity was poised to change that. Over millions of years, slight fluctuations in the density of gas clouds led to regions where the gas was denser than surrounding areas. These denser regions began to attract more and more gas, growing larger over time. Eventually, the pressure and temperature inside these dense gas clouds became so immense that nuclear fusion began, a process that powers stars. Inside these first stars, hydrogen atoms fused together to form heavier elements, including carbon, oxygen, and even iron. These elements, forged in the hearts of stars, would later become the building blocks for planets, life, and everything we know today. If the universe could emerge from nothingness once, could it happen again? Some theories suggest that our universe is just one of many in a vast multiverse, where new universes are continually created through quantum fluctuations. Others propose that the universe undergoes an endless cycle of expansion and collapse, with each new cycle giving birth to a fresh cosmos. Regardless of which theory holds true, one thing remains abundantly clear. The mere existence of atoms is nothing short of miraculous. From the emptiness of a quantum vacuum to the complex structures of galaxies, stars, and even life itself, the journey of atoms is a profound tale of transformation. The creation of matter from an initial state of nothingness is a testament to the remarkable power of nature's fundamental laws and the extraordinary changes that can occur under extreme conditions. It took billions of years for the universe to evolve from a void of pure energy into the rich and intricate cosmos we observe today. Yet even now, scientists continue to probe the deepest mysteries of how such an event could take place, struggling to fully understand how something as basic as matter can emerge from nothingness. Could there be deeper, undiscovered laws of physics lurking beneath the surface? Might the universe itself be just a tiny fragment of a much grander, more complex reality? These questions remain unanswered, but the mysteries of the universe are not merely theoretical. The forces that gave rise to the cosmos are grounded in one of the most fundamental principles of physics, Heisenberg's uncertainty principle. This principle posits that at the smallest scales of reality, it is impossible to simultaneously measure both the energy and time of a particle with perfect precision. As a result, tiny particles and energy waves constantly flicker in and out of existence, a restless dance of creation and annihilation. Even in what we would consider a complete vacuum, where no matter exists, quantum fluctuations continue to occur. Virtual particles, tiny, fleeting bits of energy, appear and vanish in an instant, only to disappear again before they can be observed directly. These fluctuations are not mere theoretical constructs. Scientists have observed their effects in numerous experiments. They are the very reason why atoms do not collapse under their own weight, and why certain particles exhibit behaviors that defy classical explanations. Before the Big Bang, these quantum fluctuations were everywhere, forming the groundwork for the universe's creation. Then, something extraordinary occurred. An event so powerful unfolded that it transformed these minute quantum ripples into the very seeds of our universe. Scientists believe that a rapid expansion, known as cosmic inflation, played a pivotal role in this process. During inflation, the universe expanded at a rate so fast it is almost incomprehensible, stretching the quantum fluctuations across vast distances. These tiny fluctuations, once confined to the microscopic scale, were now amplified and stretched, creating small density variations in the very fabric of space. As the universe continued to cool, these energy variations became the blueprint for everything that followed. The slightly denser regions of space began to attract more and more energy, forming the very building blocks of matter. In this way, quantum fluctuations, once mere flickers of uncertainty, became the foundation for everything: galaxies, stars, planets, and ultimately, life itself. In those first moments of cosmic infancy, the universe's extreme energy began to solidify into the most basic components of matter: quarks, leptons, and gluons. Quarks, the tiny particles that would later combine to form protons and neutrons; leptons, which include electrons; and gluons, which served as the glue holding quarks together, all began to take shape. Yet the universe at this stage was still a seething, hot, dense plasma, with particles colliding at unimaginable speeds. The birth of matter from these fluctuations marked the beginning of everything we now observe, an incredible transformation from nothing to the vast, complex universe we call home. However, as the universe continued to cool, something truly remarkable began to unfold. In the frigid darkness, the building blocks of matter, the quarks, began to merge, forming protons and neutrons, the very heart of atomic nuclei. This crucial development occurred roughly 380,000 years after the Big Bang, when the cosmos had cooled enough for protons and neutrons to finally capture electrons, giving rise to the first stable atoms. This epochal event, known as recombination, marked the birth of matter as we know it. The dominant element formed during this period was hydrogen, which, alongside helium, was the foundational building block of everything to come. A smaller amount of lithium also emerged, but it was hydrogen and helium that would come to dominate the universe's chemistry. At this point, the universe, which had once been a seething cauldron of high-energy radiation and particles, began to take a more structured shape. For the first time in cosmic history, light could travel freely through space, unimpeded by charged particles. This allowed for the release of what we now call the cosmic microwave background radiation, a faint but persistent glow of energy that serves as a snapshot of the early universe, carrying with it the imprint of the conditions that existed just after the Big Bang. Yet even as atoms formed, the universe remained far from what we recognize today. The early atoms, primarily hydrogen and helium, were scattered across the vastness of space, floating within immense clouds of gas. Over millions of years, gravity began to exert its influence, drawing these atoms together. The force of gravity became so intense in certain regions that it squeezed the atoms closer and closer, heating them up and igniting nuclear fusion. This was the moment the first stars were born. Inside these early stars, the process of nuclear fusion fused lighter elements like hydrogen and helium into heavier elements such as carbon, oxygen, and iron, the very elements that would later form planets and even life itself. When these early stars reached the end of their lives, they exploded in catastrophic supernova, scattering these precious elements throughout space. Over billions of years, this cosmic dust accumulated, eventually giving rise to new generations of stars, planets, and eventually Earth. It is truly awe-inspiring to think that everything around us, our very bodies, the air we breathe, and the stars that light up our night sky, can be traced back to minute quantum fluctuations in the early universe. These fluctuations, which began as tiny, seemingly random disturbances, would lay the foundation for galaxies, stars, and even life itself. Without these initial irregularities, the universe could have remained a featureless, homogeneous expanse, never developing into the rich, complex structures we see today. The universe's grandest landscapes were born from the tiniest imbalances in energy, ones that enabled matter to clump together and evolve into the vast array of forms and phenomena we now take for granted. The story of the universe is, at its heart, a tale of transformation, energy morphing into matter, simple atoms becoming intricate structures and the smallest fluctuations shaping the vast and intricate tapestry of the cosmos. Quantum fluctuations, which were once thought to be nothing more than random noise, turned out to be pivotal in this process. Even today, quantum mechanics continues to challenge and expand our understanding of reality. It teaches us that at the most fundamental level, uncertainty reigns supreme. Yet it is this very uncertainty that allowed the formation of something as vast and beautiful as the universe we inhabit. Imagine, for a moment, a world where objects can appear and disappear at will, where a single entity can exist in multiple locations simultaneously, and where the rules of classical logic seem to dissolve entirely. This is not the realm of science fiction. It is the strange and paradoxical world of quantum mechanics. Quantum mechanics, a branch of physics that describes the behavior of the tiniest building blocks of our universe, reveals a reality that defies all expectations. Unlike the world we experience daily, where objects follow predictable paths and behave according to well-established rules, the quantum world is a place of uncertainty, mystery, and bizarre behavior. At this microscopic scale, particles, the fundamental constituents of atoms, don't behave like solid, predictable objects. Instead, they exist as waves of energy, constantly shifting and fluctuating, appearing and disappearing, and even occupying multiple locations at once. This concept, known as wave-particle duality, suggests that particles can behave both as discrete objects and as waves of energy, depending on how they are observed. One of the most mind-bending phenomena in quantum mechanics is the ability of particles to vanish and reappear seemingly at random. This process, known as quantum fluctuations, occurs even in the emptiest of vacuums, where we would normally expect absolute nothingness. In these empty spaces, tiny particles, called virtual particles, pop in and out of existence in a fraction of a second. Though these fluctuations are fleeting and nearly impossible to detect directly, their effects have been observed in numerous experiments, confirming that the quantum world is far from empty. This bizarre behavior stems from the fact that, according to quantum mechanics, even empty space is far from empty. It is filled with quantum fields, invisible energy fields that extend throughout the entire universe. These fields are in a constant state of vibration, and occasionally, they create particles out of nothing, only for them to vanish again before we can observe them directly. While these virtual particles exist for a brief instant, their effects on the cosmos are profound. Scientists believe that these fluctuations, these tiny bursts of energy, played a key role in shaping the early universe. Without them, the universe might have never evolved into the complex and dynamic structure we see today. To grasp just how strange the quantum world can be, let's explore one of the most famous thought experiments in the history of physics, Schrödinger's cat. In this thought experiment, physicist Erwin Schrödinger imagined a scenario where a cat is placed inside a sealed box with a mechanism that releases poison based on the behavior of a quantum particle. According to the principles of quantum mechanics, before we open the box and observe the cat is not simply alive or dead. It is in a superposition of states, being both alive and dead at the same time. The fate of the cat is directly linked to the behavior of the quantum particle, which can exist in multiple states simultaneously. This strange phenomenon, called superposition, suggests that at the quantum level, particles can exist in multiple states at once, only choosing a specific state when they are measured or observed. While Schrödinger's cat is a thought experiment, the underlying concept of superposition has been confirmed in real experiments with subatomic particles. Electrons, photons, and other tiny particles have been observed to behave in multiple ways at once, only deciding on a particular behavior when they are measured. Even more peculiar is the concept of quantum tunneling. In the classical world, if you throw a ball at a wall, it will simply bounce off. But in the quantum realm, particles have a chance of passing through barriers as though they were ghosts. This happens because, unlike macroscopic objects, quantum particles don't behave like solid objects. They act as waves that can extend beyond physical barriers, meaning there's a small probability that a particle can tunnel through a wall and appear on the other side. Quantum tunneling is not merely a theoretical concept. It is a real phenomenon that plays a crucial role in modern technology. Transistors, the tiny switches that power your computer and smartphone, rely on quantum tunneling to function. Without this phenomenon, much of the technology we take for granted would simply not be possible. Perhaps the most puzzling and fundamental principle of quantum mechanics is Heisenberg's uncertainty principle. This principle asserts that there is a fundamental limit to how precisely we can measure certain properties of particles. For example, if we try to measure the exact position of an electron, we lose information about its speed, and if we measure its speed, we lose information about its position. This uncertainty is not due to imperfections in our instruments. It is inherent in the nature of reality itself. At the quantum level, the universe is not a fixed, predictable machine, but a constantly shifting and uncertain realm, where things exist in probabilities rather than definite states. This inherent uncertainty challenges our classical understanding of the world, revealing a reality far stranger and more complex than we could have ever imagined. One of the most mysterious and awe-inspiring phenomena in the realm of quantum mechanics is undoubtedly quantum entanglement. This perplexing concept occurs when two particles become deeply intertwined in such a way that any change or measurement made to one instantly affects the other, no matter how vast the distance between them. Imagine this. If one particle is measured and found to be spinning in a particular direction, its entangled partner, no matter how far across the universe it is, will immediately spin in the opposite direction as though bound by an invisible thread. This instantaneous transfer of information seems to defy the laws of physics as we know them, specifically the limit of the speed of light, as it happens faster than anything should be able to travel. Albert Einstein, ever the skeptic when it came to the abstract realms of quantum theory, famously dubbed this phenomenon spooky action at a distance. To him, it was an unsettling idea, something that seemed too fantastical, too absurd to fit into the neatly ordered framework of classical physics. However, quantum entanglement, though initially met with resistance and disbelief, has been repeatedly verified through countless experiments. Scientists have found that not only does it exist, but it may hold the key to breakthroughs in technology. This could lead to revolutionary advancements such as ultra-secure communication systems and even the development of quantum computers, which have the potential to perform computations far beyond the capabilities of today's classical machines. The principles behind quantum mechanics might seem almost otherworldly at first glance, but they are already transforming the future. Researchers are currently exploring ways to build quantum computers, which rely on quantum bits, or qubits, to process information in ways that classical computers could never hope to replicate. These machines harness the quirks of quantum particles, such as superposition and entanglement, to handle complex calculations at previously unimaginable speeds. The potential applications for such technology are staggering. Quantum computers could revolutionize everything from medical research and artificial intelligence to cryptography, making data secure in ways that were once thought impossible. While the idea of quantum mechanics may sound like a bizarre theory straight out of science fiction, the reality is that its principles are already beginning to shape the technological landscape of the future. Researchers are investigating how these strange quantum behaviors could be harnessed for new energy technologies, enhanced encryption systems, and perhaps even the fantastical possibility of teleportation. Although the teleportation of large objects or people remains a distant dream for now, quantum entanglement has already been used to successfully teleport small particles, hinting at the exciting potential of this technology. To fully appreciate the strangeness of quantum mechanics, we must also look at the concept of quantum fluctuations, which play a fundamental role in shaping the universe itself. The idea of nothing may seem simple on the surface, but in quantum theory, even empty space is far from empty. The quantum field, an invisible omnipresent energy field, permeates all of space, continuously fluctuating and shifting in ways that we can barely begin to comprehend. These fluctuations are tiny, momentary changes in energy that occur spontaneously within the quantum field. To visualize this, imagine a calm pond. If you throw a stone into the water, ripples form on the surface, spreading out in all directions. These ripples, in this analogy, represent quantum fluctuations. The crucial difference, however, is that unlike ripples caused by a physical object in the pond, quantum fluctuations occur without any external cause. They arise on their own, spontaneously, and vanish just as quickly, momentarily altering the energy of the quantum field before disappearing. It's almost as though space itself is alive, constantly flickering in and out of existence in a delicate dance of creation and destruction. At first, the concept of something coming from nothing might seem utterly illogical. In our everyday experiences, objects do not simply appear from thin air. However, quantum mechanics operates under a set of rules that differ drastically from our macroscopic reality. At the heart of understanding this lies the Heisenberg uncertainty principle, a cornerstone of quantum theory. This principle asserts that certain properties of particles, such as their energy and the exact moment in time when they exist, cannot both be precisely measured at the same time. Because of this uncertainty, energy can spontaneously emerge in brief bursts, seemingly out of nowhere, during fleeting moments. These bursts often give rise to pairs of particles, one of matter and one of antimatter, that exist only for a fraction of a second before vanishing again. These fleeting, virtual particles constantly pop into existence and disappear, leading us to a mind-bending conclusion. Space is never truly empty. Even in a vacuum, where there appear to be no particles, these quantum fluctuations are at play, creating and destroying particles in a constant cycle. This revelation has profound implications for our understanding of the cosmos. The very fabric of reality, it seems, is far more complex than we ever imagined. Quantum fluctuations are not mere theoretical curiosities. They play an indispensable role in the structure of the universe itself. One of the most groundbreaking ideas in cosmology is that the universe itself may have originated from a quantum fluctuation. In the moments preceding the Big Bang, scientists theorize that the universe existed in a highly unstable quantum state. A tiny fluctuation within this state might have triggered the violent explosion of energy that led to the creation of everything we know. If true, this theory suggests that the universe did not need any pre-existing cause to begin. It could have emerged spontaneously from the quantum vacuum due to the fundamental laws of physics. Moreover, quantum fluctuations have shaped the very structure of the cosmos. In the early universe, when space was rapidly expanding, tiny variations in energy, created by quantum fluctuations, caused slight differences in the density of the universe's matter. Over time, these tiny disparities in density grew, eventually giving rise to the galaxies, stars, and planets we see today. Without these fluctuations, the universe might have remained a featureless expanse, unable to develop the intricate complexity we now observe. In this sense, the entire cosmic web, the vast, interconnected network of galaxies stretching across billions of light years, owes its existence to the unpredictable nature of quantum mechanics. Even the most enigmatic objects in the universe, such as black holes, are influenced by these quantum fluctuations. The brilliant physicist Stephen Hawking proposed a fascinating theory known as Hawking radiation, which suggests that black holes gradually lose mass over time due to quantum processes. In simple terms, quantum fluctuations create pairs of virtual particles at the event horizon of a black hole. One particle falls into the black hole while the other escapes into space. This process causes the black hole to lose a tiny bit of mass, and over an immense period of time, it could eventually result in the black hole's complete evaporation. You may be wondering, do quantum fluctuations have any bearing on our everyday lives? While their effects are generally too subtle for us to notice directly, they do influence several real-world phenomena. One striking example is the stability of atoms. Quantum fluctuations play a pivotal role in determining the behavior of subatomic particles, which in turn affects how atoms interact with one another. Without these fluctuations, the fundamental forces of nature might operate differently, and matter, as we know it, might not exist in the form we recognize. Another fascinating application of quantum fluctuations is found in the realm of quantum computers. These advanced machines take advantage of the strange properties of quantum mechanics to process information in ways that traditional computers cannot. By harnessing quantum fluctuations, scientists are developing computers that could revolutionize fields like cryptography, artificial intelligence, and scientific research, solving problems that are currently beyond our reach. There is even a provocative theory that suggests if small quantum fluctuations can create particles, might it be possible for a much larger fluctuation to create an entirely new universe? This idea, known as the theory of eternal inflation, posits that our universe is just one of many, continuously emerging from quantum fluctuations in an ever-expanding cosmic space. In this view, new universes could be constantly coming into existence, each governed by its own set of physical laws and properties. The notion that something can emerge from nothing challenges our deepest understanding of reality itself. These quantum fluctuations, small as they may be, hold profound implications for the nature of existence. They have influenced everything from the smallest particles to the grandest galaxies, and may even have played a role in the very birth of the universe. While much about quantum physics remains shrouded in mystery, one thing is certain: the idea that something can arise from nothing is not just a curious thought experiment, but a fundamental aspect of how our universe operates. In the early moments of the universe, as energy collided and transformed in a boiling cauldron of cosmic potential, the process of quantum fluctuations paved the way for the formation of atoms, those tiny building blocks that make up everything we see, touch, and experience. Without this delicate interplay of energy, matter, and time, the universe as we know it might never have come to be. Energy is the lifeblood of the universe, constantly in motion, ever-changing. But even in this constant flux, it wasn't distributed evenly. Some regions of space held slightly more energy, while others held slightly less. These small imbalances, often imperceptible to the human eye, were not trivial. In fact, they were pivotal to the shaping of the cosmos, creating the seeds of everything that would follow. These fluctuations, minute variations in energy and density, acted as the invisible architects of the universe's grand design. To understand these fluctuations, one must delve into the very fabric of the universe, where the laws of quantum mechanics reign supreme. In this microscopic realm, energy and matter are never perfectly uniform. Even in the emptiest seeming spaces, quantum mechanics dictates that there are always tiny, unpredictable variations, fluctuations that reverberate through space and time. These ripples, imperceptible on their own, would eventually become the foundation for the formation of everything we know: galaxies, stars, and even the atoms that make up our bodies. In the earliest moments of the universe, during the incredibly hot and dense phases of its infancy, space itself began to stretch. The fluctuations from quantum mechanics were not left to dissipate, they were amplified. As the universe expanded, areas of space with slightly higher energy density grew denser, while regions with less energy became more sparse. What began as minor differences in energy distribution grew into the cosmic structure we now observe. Over eons, these variations would dictate the formation of everything from the smallest atoms to the largest galaxies. Energy and matter were inextricably linked. As the universe cooled and expanded, energy began to convert into matter, an event described by Albert Einstein's famous equation E=mc². However, this transformation wasn't smooth. It was highly dependent on the earlier fluctuations that had left certain regions with more energy. In these areas, particles formed at a higher rate, giving rise to the first subatomic particles. Within fractions of a second, quarks and gluons, the building blocks of matter, began to combine, giving rise to protons and neutrons, elements that would later form atomic nuclei. But the universe was still too hot for stable atoms to form. Protons and neutrons needed electrons to join them and create atoms, but the temperatures were so high that electrons moved at incredibly fast speeds, making it nearly impossible for them to be captured by nuclei. Instead, the universe was filled with a dense plasma-like soup where photons, particles of light, were constantly scattering off these free electrons, preventing light from traveling freely. Then, after hundreds of thousands of years, as the universe cooled, the temperature dropped enough for electrons to slow down and bond with protons and neutrons. This moment, known as recombination, marked the birth of the first atoms. For the first time in cosmic history, light could travel freely across the universe. This light, now known as the cosmic microwave background, CMB, serves as a faint echo, a snapshot of the universe in its infancy. In the wake of recombination, hydrogen and helium, two of the simplest elements, formed the majority of the universe's atomic content. Over the next few billion years, gravity began its work. Hydrogen and helium atoms, pulled together by gravity, coalesced into massive clouds of gas. These gas clouds collapsed under their own weight, leading to the formation of the first stars and galaxies. In a universe that had initially been in a state of near-perfect uniformity, the fluctuations were crucial. Without these small differences in energy density, gravity would have had nothing to pull on. Without gravity's influence, matter would have remained evenly spread across space, leaving no room for the formation of the structures we see today. The universe, in its chaotic infancy, was teeming with potential. These fluctuations acted like tiny seeds, providing the gravitational nudge necessary for matter to gather and form the first stars. Stars, in turn, began to forge heavier elements, carbon, oxygen, and iron, creating the essential building blocks for life as we know it. One way scientists and philosophers often conceptualize the universe is as a chaotic, bubbling soup, a mixture of elementary particles and raw energy constantly interacting. But what are these elementary particles? These are the fundamental pieces of matter: electrons, protons, and neutrons. But even these are made up of even smaller particles, quarks and leptons, which are the true building blocks of everything in the universe. These particles are so minuscule that they cannot be seen with the naked eye, or even with most microscopes. They exist in a domain entirely separate from the everyday world we experience. Imagine a bustling city where everything is in motion. Cars, people, buses, all rushing in different directions. In the quantum realm, particles are like this, constantly in motion, interacting and colliding in ways that are completely unpredictable. This constant movement, this chaotic dance of particles, is the heartbeat of the universe. Even though we cannot always predict the behavior of individual particles, we know that the universe is never still. Energy plays a vital role in this dance. It is the force that drives everything. Without energy, there would be no movement, no interaction, no change. Energy exists in countless forms: light, heat, motion, and is the reason particles interact in the first place. It flows through every part of the universe, enabling particles to collide, change, and evolve. Just as a pot of soup contains various ingredients that mix together to create something new, the universe is a vast, dynamic system where energy and particles are forever in motion. In this metaphorical soup, energy can appear in many forms. Some of it is visible to us, like light. Other forms, like gravitational energy or the energy hidden in atoms, are invisible. Still more elusive are the mysterious forces known as dark energy and dark matter. These are believed to make up most of the universe, yet we still don't fully understand them. Dark energy is thought to drive the accelerated expansion of the universe, pushing galaxies away from one another. Dark matter, on the other hand, is thought to provide the gravitational pull that prevents galaxies from flying apart, even though their stars are spinning at incredible speeds. At the quantum level, the soup of particles takes on even stranger properties. Particles can behave like both waves and particles at the same time. They can exist in multiple places at once or disappear from one location and reappear in another. The strange behaviors of quantum particles shatter our classical understanding of space and time. In this quantum world, the laws we are familiar with cease to apply, creating an even greater sense of mystery and chaos. Zooming out to the larger scale of the universe, these same particles and energies give rise to everything around us. The formation of stars, planets, galaxies, and black holes all stems from this chaotic soup of energy and particles. Gravity, one of the fundamental forces, plays a central role in holding everything together. But even gravity's influence is not always predictable. For instance, black holes are formed when massive stars collapse under their own gravity, compressing matter and energy into an infinitely small space. The gravity in these regions is so intense that it warps space and time itself, creating some of the most mysterious and extreme environments in the universe. On a grand scale, the universe is a realm of constant change. The universe is expanding, but this expansion is not uniform. Different regions of space expand at different rates. Stars are born, live, and die in dramatic supernova explosions. Galaxies are born, collide, and merge. Even black holes, the most mysterious objects in space, are in a state of continuous flux. Over billions of years, these chaotic processes have shaped the cosmos into what we see today. and continue to shape the universe in ways we are only beginning to understand. Despite the chaos, there is a sense of order to it all. The laws of physics, gravity, electromagnetism, and nuclear forces govern the interactions of particles and provide the framework for the universe's structure. These laws create the conditions under which stars, planets, and galaxies can form, but they also allow for the unpredictability and complexity that make the universe so intriguing. It is this delicate balance between order and chaos that makes the universe both predictable and mysterious at the same time. As the universe cooled, particles began to condense. Quarks, the building blocks of matter, began to form. These early moments of cosmic history, full of chaos and fluctuation, would eventually give rise to the universe as we know it, a universe teeming with stars, galaxies, and the potential for life. The early moments of the universe were defined by intense heat and pressure, a state so extreme that matter as we understand it could not exist. Instead, the universe was an undifferentiated mass of pure energy, an immensely hot and dense concentration of energy with no atoms, no particles, not even stars or galaxies. This state persisted for a fraction of a second, but as the universe expanded, it began to cool, just enough to allow the first particles to form. At the outset, the universe's temperature was so high that it was composed only of the most fundamental building blocks of matter, quarks, the tiniest known particles. These quarks were unable to bind together to form stable protons or neutrons due to the extreme energy present. It would take cooling, slow, gradual cooling, for these quarks to combine into more stable forms. As the universe expanded, the temperature slowly began to drop, allowing quarks to stick together, forming protons, which are positively charged, and neutrons, which are neutral. This moment in the universe's history was pivotal. The formation of these basic particles set the stage for everything to come. As the universe continued to cool, it began to evolve in ways that would lead to the creation of the first atomic nuclei. A few minutes after the Big Bang, a process known as nucleosynthesis took place. This was when protons and neutrons fused together to form the simplest nuclei: hydrogen, helium, and small amounts of lithium. These first nuclei were the foundation for everything that would follow. However, the universe was still far from the peaceful, orderly cosmos we know today. The temperatures remained high enough that electrons, which had already begun to form, could not yet combine with these nuclei to create stable atoms. Instead, the universe was filled with a chaotic soup of particles, light, and radiation, all in a constant state of interaction. In these early moments, particle-antiparticle pairs were created and annihilated in a never-ending cycle. This chaotic process continued for several more minutes until the universe cooled enough to allow more stable particles like protons and neutrons to remain intact. As the cooling continued, conditions became more favorable for the formation of neutral atoms. By about 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons to finally combine with protons and neutrons, forming hydrogen and helium atoms. This marked a monumental shift. The universe, once a dense and foggy soup of particles, became transparent. For the first time, light photons could travel freely through space. This event, called the era of recombination, released the cosmic microwave background, CMB radiation, a faint glow that we can still detect today, providing us with a glimpse of the universe's earliest moments. With the formation of these neutral atoms, the universe entered a new phase of evolution. Gravity began to take its toll, and the hydrogen and helium atoms began to clump together, slowly forming larger structures. The pressure and temperature were now lower than before, but gravity's influence began to pull these atoms together, eventually leading to the formation of stars. These stars, the first of their kind, were born from the gathering and compression of gas clouds. As gravity continued to compress the gas, temperatures soared, eventually triggering nuclear fusion, the process that powers stars. In the hearts of these stars, fusion reactions occurred at staggering temperatures, creating new, heavier elements like carbon, oxygen, and even iron. The formation of these elements within stars was a crucial step in the ongoing evolution of the universe. But stars don't last forever. When they run out of fuel, they can undergo a massive explosion known as a supernova. This explosion scatters the elements they have created into space, enriching the universe with the building blocks for new stars, planets, and eventually, life. The heavy elements created in these stellar explosions, such as gold, platinum, and uranium, are fundamental to the formation of planets and life as we know it. This process of star formation and supernovae continued for billions of years, gradually enriching the universe with more and more complex elements. Stars created heavier elements through fusion, and when they died, they spread these elements across the cosmos. As the universe cooled and stars died, the elements they had created gathered together, forming new stars, galaxies, and planets. This cycle of stellar birth, life, and death played a crucial role in shaping the universe into the complex, structured system we observe today. As the universe continued to cool, its evolution didn't stop. Matter continued to gather due to the force of gravity, and over billions of years, stars formed, galaxies coalesced, and the universe as we know it took shape. But this cooling process, while slowed considerably, is not over. The universe is still expanding, still cooling, and still evolving. And as it does, it will continue to evolve in ways we may not yet fully understand. One of the most profound insights we have about the early universe comes from studying the cosmic microwave background, CMB, the remnant radiation from the Big Bang. This faint glow carries the history of the universe's infancy, offering us a unique window into the past. By studying the CMB, scientists can learn more about the universe's early conditions, its rapid expansion, and the gradual formation of matter and structure. In many ways, the cooling of the universe is still ongoing. While the rate of cooling has dramatically slowed since the Big Bang, it continues. As the universe expands, galaxies move farther apart, and the space between them grows ever larger. This expansion is not only a continuation of the cooling process, but also an indication of the universe's ongoing evolution. In time, new stars will continue to form, new galaxies will emerge, tech and new discoveries will undoubtedly unfold as we look deeper into space. The cooling of the universe and the transformation from pure energy into matter is a story that spans billions of years. From the earliest moments when the universe was a hot, dense ball of energy, to the formation of the first atoms, stars, and galaxies, the process has been gradual but transformative. Every element in the universe, from the atoms that make up the air we breathe to the stars that light the night sky, originated from this transformation. The cooling process is the cornerstone of the universe's development, a slow but inexorable path from chaos to order. This narrative is also deeply connected to one of the most famous equations in physics, Einstein's equation, E equals mc squared. This formula represents the energy-mass equivalence principle, one of the cornerstones of modern physics. It tells us that energy and mass are not separate but interchangeable. In the context of the Big Bang, this principle is key to understanding how energy transformed into matter. The early universe was composed of pure energy, and as it cooled, this energy condensed into particles, protons, neutrons, and electrons. These particles formed the first atoms, and from these atoms, stars and galaxies formed. The equation E equals mc squared reflects the inherent connection between energy and mass. When we look at the formation of atoms in the early universe, we see energy being converted into mass, creating the particles that would form atoms. These atoms, in turn, created the stars, which were responsible for forging the heavier elements that would eventually make up planets, rocks, and ultimately, life. The entire process of the universe's evolution, its cooling, its expansion, its transformation from energy into matter, can be understood through the lens of this simple yet profound equation. As we stand on the shoulders of this vast cosmic history, it's awe-inspiring to realize that the universe is still evolving, still cooling, and still expanding. Each moment adds a new chapter to this incredible journey that began over 13.8 billion years ago. And as we continue to study the cosmos, we uncover new layers of understanding about the forces that shaped everything we see and everything we are. Energy, in its purest form, is a force that shapes the universe in ways that are both mysterious and essential to the very existence of everything around us. When the Big Bang occurred, it unleashed an extraordinary amount of energy into the cosmos, setting the stage for the formation of the universe as we know it. However, this wasn't just energy in the form of light or heat. No, it was much more profound. This energy transformed into mass, giving birth not only to the particles that make up matter, but also to the forces that hold those particles together. The electromagnetic force, the strong nuclear force, and the weak nuclear force, each playing a vital role, began to dictate how particles interacted with each other. At the heart of this monumental transformation is a revolutionary concept introduced by Albert Einstein, his famous equation E equals mc squared. This simple but powerful equation reveals that energy and mass are two sides of the same coin. As the universe began to expand and cool, the raw energy from the Big Bang began to condense into mass. However, this mass didn't immediately form into the atoms we recognize today. Instead, it eventually gathered to create the simplest elements in the universe: hydrogen and helium. These elements would become the building blocks for everything that exists in the cosmos. As the universe cooled, the particles that had formed from the Big Bang began to interact in increasingly complex ways, eventually forming atomic nuclei, protons and neutrons clustering together to form the very cores of atoms. But the universe was still far too hot for fully formed atoms to emerge. In this sweltering environment, particles like protons and neutrons collided and fused to create the first nuclei, mostly hydrogen and helium, with tiny traces of other elements. It wasn't until the universe cooled sufficiently, about 380,000 years after the Big Bang, that electrons could slow down enough to be captured by these nuclei, forming the first neutral atoms in a process known as recombination. The role of Einstein's equation in this grand process cannot be overstated. The speed of light, appearing in his equation, is not just a number. It is a constant that governs how energy and mass interact. The enormity of the speed of light, when squared, reveals how even a tiny amount of mass can be converted into an immense amount of energy. This relationship between energy and mass is at the core of understanding nuclear reactions, like the fusion happening in the hearts of stars, or the creation of particles during the earliest moments of the universe. During the earliest period of the universe, energy wasn't just turning into particles one by one. It was a dynamic, high-energy environment where particles collided, transformed, and converted back and forth between energy and mass. In these extreme conditions, energy often manifested as radiation, light and heat traveling at the speed of light, shaping the formation of matter in ways we can still study today. One of the clearest examples of energy converting into mass was nuclear fusion. This process, which still powers stars like our sun, is where lighter atomic nuclei fuse to form heavier ones, releasing massive amounts of energy in the process. In the early universe, the energy from the Big Bang caused particles to move so rapidly, colliding with such force, that fusion was inevitable. For example, protons, the nuclei of hydrogen, fused to create helium nuclei in a process known as primordial nucleosynthesis. This fusion happened within the first few minutes after the Big Bang, when the universe was still an incredibly hot and dense soup of particles. The particles' energy was so immense that, as Einstein's equation predicted, it was sufficient to overcome the repulsive forces between them, allowing them to merge and form heavier elements. The energy released in these reactions didn't just create mass. It laid the groundwork for the stars, galaxies, and ultimately the atoms that make up everything we observe today. At this point, we enter the realm of the atomic structure itself. Atoms, the basic building blocks of all matter, consist of a nucleus made up of protons and neutrons surrounded by a cloud of electrons. The intricate dance between these particles and the forces that govern them is what defines the nature of everything in our universe. The electromagnetic force, for instance, governs how electrons are attracted to protons, forming stable atoms. These forces, along with the strong nuclear force, which binds protons and neutrons together in the nucleus, are direct results of the conditions created by the Big Bang's energy. Yet, while we have a broad understanding of how energy morphed into matter, the question of how pure energy itself became the complex and varied matter we see today remains a profound mystery. This transformation wasn't instantaneous, it took time. In the first moments following the Big Bang, the universe was so hot and dense that particles couldn't combine to form stable matter. Instead, they existed in a high-energy plasma, moving at incredible speeds. As the universe cooled, the conditions finally allowed quarks to bind together to form protons and neutrons, and for electrons to begin forming around them. This marked the first true steps toward the creation of atoms. This conversion of energy into matter was only possible due to the fundamental forces of nature, which dictate how particles interact with one another. The strong nuclear force, one of the most powerful forces in the universe, was crucial in holding quarks together to form protons and neutrons. The electromagnetic force then took over as the universe cooled, allowing electrons to bond with protons, forming the simplest atoms, hydrogen, the most abundant element in the universe. But the transformation didn't stop there. As the universe continued to cool, it began to evolve in more intricate ways. Clouds of gas collapsed under gravity, forming the first stars. Inside these stars, nuclear fusion continued, fusing lighter elements like hydrogen and helium to form heavier elements. This process, which powers stars even today, releases immense amounts of energy, shaping the evolution of galaxies and planets. These newly formed elements spread across the universe, contributing to the formation of everything from new stars to the planets and life forms that would one day arise. However, even as we gain a deeper understanding of how energy turned into matter, we are still confronted with the unknown. One of the greatest enigmas facing modern cosmology is the nature of dark matter. This mysterious substance does not emit, absorb, or reflect light, making it invisible to our current instruments. Yet, it is believed to make up around 27% of the universe. We cannot see dark matter directly, but its gravitational effects are evident, suggesting its presence. How dark matter formed from pure energy remains one of the great puzzles in science. Even more perplexing than dark matter is dark energy, a force believed to be responsible for the accelerated expansion of the universe. Dark energy accounts for roughly 68% of the universe's total energy, yet scientists have very little understanding of its nature or how it works. Some theories speculate that dark energy could be connected to the energy that filled the universe in its early moments, but this remains highly speculative. As the universe continues to evolve, the process of energy transforming into matter is still unfolding. Over billions of years, energy has led to the formation of stars, planets, and galaxies, and eventually to life itself. From the very first moments of the Big Bang to the complex and diverse cosmos we observe today, the transformation of energy into mass has been the driving force behind the creation of everything. From the vast expanse of the stars above us to the intricate dance of atoms within our bodies, the transformation of radiation into fundamental particles such as protons, neutrons, and electrons is one of the most captivating phenomena in the universe. It unfolds in environments both familiar and alien, from the heart of a star to the cold, distant reaches of space. Understanding this process requires us to explore the very essence of radiation and how, in certain conditions, it can give birth to the building blocks of matter. Radiation, at its core, is a form of energy that propagates through space in the shape of waves or particles. It can emerge from a variety of sources: the blazing heat of the sun, the radioactive decay of elements in Earth's crust, or even the cosmic rays that travel from the depths of outer space. Radiation is not a single entity. It exists in multiple forms, each with unique characteristics. There's light, heat, X-rays, and gamma rays, to name a few, as well as highly energetic particles like cosmic rays that hurtle through space at nearly the speed of light. The most fascinating aspect of radiation, however, is its ability to occasionally transform into tiny particles, the very building blocks of matter. These particles include protons, neutrons, and electrons, each playing a crucial role in the structure of atoms. Protons, which carry a positive charge, are found in the nucleus of every atom. The number of protons in an atom's nucleus determines its identity as a particular element. For example, a hydrogen atom contains just one proton, while helium has two. Neutrons, which are neutral particles without charge, also reside in the nucleus, contributing to the atom's mass and playing an important role in stabilizing the nucleus. Electrons, on the other hand, are negatively charged particles that orbit the nucleus. Though they are much lighter than protons or neutrons, they are essential to chemical reactions and the flow of electricity. But how exactly does radiation lead to the creation of these subatomic particles? It all begins with high-energy radiation, such as gamma rays or cosmic rays, interacting with matter. When these high-energy waves or particles collide with atoms, they can cause those atoms to break apart or undergo transformations, converting energy into new forms, including protons, neutrons, and electrons. One key process in this transformation is known as pair production. Pair production occurs when a high-energy photon, a particle of light or radiation, encounters a strong electromagnetic field, typically near the nucleus of an atom. If the photon's energy is sufficiently high, it can convert into a pair of particles, an electron and a positron, the antimatter counterpart of the electron. This process is a vivid illustration of Albert Einstein's famous equation E equals c squared, which shows that energy and mass are interchangeable. In this case, the energy of the photon is transformed into the mass of the particle-antiparticle pair. Another way radiation leads to particle creation is through high-energy collisions. For instance, when cosmic rays, particles traveling from space at nearly the speed of light, strike Earth's atmosphere, they collide with the atoms in the air. These collisions break apart the atoms and produce new particles, including protons, neutrons, and electrons. This is the origin of the showers of secondary particles that are detected by instruments on the ground. Similarly, in particle accelerators, scientists deliberately accelerate particles to speeds approaching the speed of light and make them collide, creating new particles in the process. In addition to these laboratory experiments, radiation also plays a central role in the creation of particles during natural nuclear reactions, such as those occurring in the sun or in nuclear reactors. In these reactions, large atomic nuclei break apart or combine, releasing massive amounts of energy in the form of radiation. This radiation can then trigger further reactions that produce particles like protons and neutrons. For example, when a neutron collides with a nucleus in a reactor, it can cause the nucleus to split, releasing more particles and radiation in the process. The conversion of radiation into particles is not confined to laboratories or reactors. It's a phenomenon that occurs all around us, especially in the vast expanse of outer space. Stars, including our own sun, produce enormous amounts of radiation, much of which is in the form of high-energy gamma rays and X-rays. These rays interact with particles in space, leading to the creation of new particles. And this process has been instrumental in shaping the universe as we know it today. Even the mysterious realms of black holes are not exempt from this process. When matter is pulled into a black hole, it is subjected to extreme radiation. This intense environment can result in the creation of various particles, a phenomenon that remains one of the most intriguing aspects of astrophysics. And it doesn't stop there. Even in the empty void between stars, cosmic radiation is constantly at work, generating new particles and influencing the behavior of galaxies. Everything around us, our planet, the air we breathe, the ground beneath our feet, and the stars overhead, was once forged in the heart of the universe through an incredible process known as nucleosynthesis. This is the process by which atoms are created, beginning in the earliest moments of the universe and continuing in stars during massive cosmic explosions, and even in the quiet depths of interstellar space. Imagine the universe at its inception, a hot, dense, and chaotic place. This was the era of the Big Bang, an event that set everything into motion. In the first few minutes following the Big Bang, the temperatures were astronomically high, and tiny particles, nucleons, protons, and neutrons moved at unimaginable speeds, constantly colliding and fusing together. During this brief yet critical period, known as Big Bang nucleosynthesis, the very first atomic nuclei were formed. But because the universe was expanding rapidly, it cooled down just as quickly. After about 20 minutes, the temperature had dropped enough that further nuclear reactions were no longer possible. By this time, the universe was made up almost entirely of hydrogen and helium, the two lightest and most abundant elements. A tiny fraction of lithium and deuterium, a heavier form of hydrogen, also formed. But how did all the other elements, oxygen, carbon, gold, and iron, come to be? The answer lies in the life cycles of stars. Stars are not just distant lights in the sky, they are massive natural nuclear reactors where new elements are created in the fiery cores of these celestial bodies. This process is called stellar nucleosynthesis. A star is born when a large cloud of hydrogen gas collapses under the force of gravity, igniting nuclear fusion in its core. This fusion process fuses hydrogen atoms together to form helium, releasing immense amounts of energy in the process. This is what makes stars shine. As stars age and grow hotter, they begin to fuse helium into heavier elements like carbon, oxygen, neon, and silicon. In the most massive stars, this fusion process continues, forming elements all the way up to iron and nickel. These elements are then released into space through stellar winds or violent supernova explosions, seeding the universe with the building blocks of planets, life, and everything in between. However, something fascinating occurs at a pivotal stage in a star's life cycle. Once a star begins producing iron, nuclear fusion can no longer generate energy in the same way it did with lighter elements. This inability to release energy destabilizes the star, causing it to collapse under its own weight. For the largest of these stars, the result is one of the most awe-inspiring events in the universe, a supernova explosion. A supernova is a colossal stellar explosion, an event so powerful that it can briefly outshine an entire galaxy. This explosion occurs when a massive star reaches the end of its life, and the core, unable to support itself, collapses, leading to an explosion that tears the star apart. During this cataclysmic event, the star hurls vast amounts of the elements it has formed throughout its lifetime into space. This dispersal not only enriches the cosmos with these materials, but also contributes to the formation of new celestial bodies. Among these scattered elements are the building blocks of life as we know it, from lighter substances to heavier elements that would go on to shape planets and, eventually, life itself. But the story doesn't end there. Supernovae are also responsible for the creation of entirely new elements through extremely intense nuclear reactions that occur in the heart of the explosion. In this chaotic split-second environment, atomic nuclei collide and merge in ways that would be impossible under normal conditions. These violent collisions forge elements that are far heavier than iron, including precious metals such as gold, platinum, and even uranium. One of the most important processes that takes place during this event is the rapid neutron capture process, or R process. In this process, atoms absorb a large number of neutrons in a very short time, allowing them to grow into much heavier elements. Supernovae serve as a key site where this process occurs, allowing the universe to create elements that would otherwise be impossible to form under more stable conditions. More recently, scientists have made remarkable discoveries that suggest another cosmic event is also responsible for producing heavy elements: neutron star mergers. Neutron stars are incredibly dense remnants of massive stars that have exploded as supernovae. When two neutron stars spiral towards each other and collide, they release an incredible burst of energy along with massive amounts of neutron-rich material. This environment is ideal for the R process, making neutron star collisions a significant source of some of the rarest and heaviest elements in the universe, including gold, platinum, and rare earth metals. In fact, it is believed that much of the gold in the jewelry we wear and the uranium used in nuclear power plants may have originated from such cataclysmic cosmic crashes that occurred billions of years ago. But not all elements are created in stars or during their explosive deaths. Some are formed through an entirely different process known as cosmic ray spallation. Cosmic rays are high-energy particles, mostly protons, traveling through space at nearly the speed of light. When these particles collide with atoms floating in space, they break them apart, creating new, lighter elements in the process. This is how rarer elements such as beryllium, boron, and lithium are formed. Cosmic ray spallation happens not only in the vast emptiness of deep space, but also within our own solar system, including on asteroids, meteoroids, and even in Earth's atmosphere. In fact, some of the rare isotopes found on Earth, known as cosmogenic nuclides, are the result of this ongoing process. While the majority of the universe's elements were created inside the hearts of stars, Earth itself continues to produce new atomic nuclei through a much slower and more subtle process: radioactive decay. This process occurs when unstable atoms, known as radioisotopes, gradually break down over time into lighter elements. For example, uranium, thorium, and potassium-40, all of which have existed since Earth's formation, continue to decay, releasing radiation and transforming into different elements in the process. This slow release of energy is what drives some of the heat inside our planet. contributing to volcanic activity and the movement of tectonic plates. Every element in your body, every metal in your phone, and every drop of water in the ocean came from one of the universe's grand nuclear factories, the Big Bang. The hearts of stars, supernova explosions, neutron star mergers, and cosmic rays. The universe is a vast recycling system, continuously forging, destroying, and reshaping elements over billions of years. Even today, new stars are forming from the remnants of older ones, continuing the never-ending cycle of element creation. And perhaps billions of years into the future, the atoms from our own sun will one day become part of new planets, new life forms, or even another intelligent civilization, gazing at the stars and wondering where it all began. A mere few minutes after the Big Bang, the universe had cooled enough for protons and neutrons to begin sticking together, forming the very first atomic nuclei. This process, known as Big Bang nucleosynthesis, resulted in the creation of the lightest elements: hydrogen, helium, lithium, and beryllium. These were the only elements formed in significant amounts during this early phase, as the extreme conditions required to form heavier elements, like carbon and oxygen, simply didn't exist. One key limitation was time. As the universe expanded rapidly, temperatures and densities dropped, causing the fusion process to shut down after only about 20 minutes. While the Big Bang gave the universe its first batch of elements, it was the stars that would later become the true factories of heavier elements. The first stars began to form around 500 million years after the Big Bang, fueled by the hydrogen and helium that remained from the universe's birth. Inside these stars, under extreme heat and pressure, nuclear fusion occurred. Hydrogen atoms fused into helium, and later, as the stars aged, helium fused into even heavier elements like carbon, oxygen, and nitrogen. It was within these stellar furnaces that carbon, the element essential for life, finally came into existence, something that could never have happened during the Big Bang itself. However, not all stars were capable of producing elements heavier than carbon. It took the violent death of massive stars through supernovae to create the even heavier elements such as iron, gold, and uranium. When these stars exploded, they released an enormous burst of energy that facilitated the rapid fusion of elements heavier than iron. Interestingly, some of the lighter elements, such as lithium, beryllium, and boron, were not just formed in the Big Bang, but also created much later through cosmic rays. Cosmic rays, the high-energy particles, mostly made of protons, travel through space at nearly the speed of light. When they collide with atoms in interstellar gas and dust, they break them apart, a process known as cosmic ray spallation. This ongoing process means that even billions of years after the Big Bang, these lighter elements continued to form in space. The creation of elements heavier than iron required even more extreme conditions than those found in normal stars. Some of these heavier elements, including gold, platinum, and uranium, were formed during the mergers of neutron stars. Neutron stars are the ultra-dense remnants of massive stars that exploded as supernovae. When two neutron stars collide, they release an extraordinary amount of energy, triggering nuclear reactions that produce some of the rarest and most valuable elements in the universe. The story of the elements that make up the universe, everything from the air we breathe to the gold in our jewelry, is one of both mystery and revelation, a saga that stretches back billions of years. It begins with the atomic nuclei forged in the heart of stars, their fundamental building blocks dispersed throughout space through cosmic events like supernovae and the collisions of neutron stars. These cosmic processes have shaped not only the matter that forms our planet, but the very life we experience. One key element in this grand tale is argon-40, a noble gas found on Earth that was produced through a natural process called radioactive decay. Radioactive decay occurs when unstable atomic nuclei break down over time, changing into different elements. This is a process that has been happening for billions of years, slowly transforming the face of our planet and adding complexity to Earth's composition. In fact, the creation of elements across the cosmos is a deeply intricate dance of nuclear reactions, cosmic rays, and geological processes. It is these forces that have fashioned the universe as we know it. From the smallest atoms to the largest stars, the field of nuclear astrophysics, the study of how elements form, has evolved into a crucial area of research, with scientists seeking to unravel the mysteries of element creation. By studying stars, supernovae, and the mergers of neutron stars, researchers are gaining insight into the very processes that gave birth to the elements scattered throughout space. The Big Bang, which marks the earliest moment in the history of the universe, was a pivotal event in the formation of elements. Yet, the tale of nucleosynthesis, the creation of new elements, has been unfolding ever since, continuing even today. Through stellar processes, cosmic explosions, and the actions of high-energy particles, these elements have been distributed across vast regions of space, eventually forming the structures we observe. From the galaxies far beyond to the DNA molecules in our bodies. Everything around us, from the stars to the very soil beneath our feet, is made of elements that have been born out of fire and violence. At the beginning of scientific inquiry, the origin of these elements was an unsolved mystery. Early theories suggested that all the elements we know today were created in the very first moments of the universe's existence. But as research progressed, it became clear that this explanation was insufficient. Through observation and data collection, scientists began to identify certain patterns. Hydrogen and helium, the lightest of the elements, were by far the most abundant in the universe, making up nearly all of its known matter. In fact, these two elements are the building blocks of almost every star, planet, and galaxy. All other elements, such as oxygen, carbon, and iron, constitute less than 2% of the mass of our solar system and others across the cosmos. But something else stood out as well. Scientists found that oxygen and carbon were the next most common elements after hydrogen and helium. And there was another curious observation. Elements composed of whole numbers of helium-4 nuclei, referred to as alpha particles, were notably more abundant. The question was, where did these elements originate? In 1920, a bold hypothesis emerged from British astrophysicist Arthur Stanley Eddington, who proposed that stars produce their immense energy by fusing hydrogen atoms into helium. Not only that, but Eddington also speculated that stars could be the very factories where heavier elements were formed. At that time, though, scientists lacked the understanding of nuclear fusion, and his idea was not widely accepted. Yet, Eddington's proposition set the stage for later breakthroughs. In the years that followed, key advances were made. Before World War II, German-American physicist Hans Bethe unraveled the exact nuclear reactions responsible for powering stars. He explained how, under extreme pressure and heat, hydrogen atoms could fuse together inside a star's core, forming helium and releasing massive amounts of energy. This process, nuclear fusion, is the engine that fuels stars and allows them to shine for billions of years. After the war, British scientist Fred Hoyle expanded upon Bethe's work and addressed a far more profound question. How do stars create heavier elements like carbon, oxygen, and iron? Hoyle proposed that all the elements heavier than helium are synthesized inside the cores of stars. As these stars evolve and pass through various stages of their life cycles, they act as cosmic furnaces, fusing lighter elements into heavier ones. Eventually, when these stars explode in supernovae, they scatter these newly forged elements across the cosmos, enriching the universe with the building blocks essential for the formation of planets and the emergence of life. But Hoyle also had a radically different view of the universe. He proposed that hydrogen itself was continuously being created out of the vacuum of space. This idea formed the foundation of his steady-state theory, which argued that the universe did not have a single beginning, but was instead in a state of constant creation. This theory stood in stark contrast to the emerging concept of the Big Bang, which suggested that the universe had a definite beginning. Interestingly, Hoyle himself coined the term Big Bang in 1949 during a BBC radio broadcast, though he used it to mock the theory that opposed his own. Over time, however, the Big Bang theory gained traction, and it helped explain why hydrogen and helium were so abundant in the universe, as well as why certain light elements, such as deuterium and lithium, were present in measurable quantities. Meanwhile, Hoyle's research on stellar nucleosynthesis illuminated how the heavier elements formed within the stars themselves. In the 1950s and 1960s, Hoyle's ideas were expanded upon by other brilliant scientists, including William A. Fowler, Alistair G. W. Cameron, and Donald D. Clayton. Their work built upon the foundation of Hoyle's discoveries and created a clearer picture of how stars evolve and produce the elements that form the matter of our universe. One of the most influential papers in this area was published in 1957 by E. Margaret Burbidge, Jeffrey R. Burbidge, William A. Fowler, and Fred Hoyle. Known as the B2FH paper, after the initials of the authors, it became a cornerstone of modern astrophysics. This seminal work outlined the various nuclear processes that occur inside stars, transforming one element into another and fueling the life cycle of stars. Simultaneously, scientists were studying the natural abundances of elements in meteorites, examining the distribution of elements in the universe. Researchers like H. Seuss and Harold Urey created a table of elemental abundances, plotting them on a graph that revealed a jagged, sawtooth-like pattern. This pattern suggested that some elements were much more common than others, offering critical insights into how elements formed in different environments, whether in the hot, dense cores of stars or in the explosive aftermath of supernovae. In the end, the story of the elements that compose the universe is not just the story of what is, but of how it all came to be. Through the fusion of light elements in stars, the explosions that scatter them into space, and the ongoing processes that continue to shape the cosmos, we have the universe we see today. A universe that, though vast and ancient, is still alive with the energy of creation. The journey of understanding where the elements that compose everything around us come from has been one of the most fascinating quests in modern science. Today, scientists have unlocked many of the mysteries behind this process, known as nucleosynthesis, which is responsible for the creation of the elements from the simplest forms of matter to some of the heaviest substances in the universe. Stars, in all their magnificence, play a central role in this cosmic cycle. The size and life stage of a star determine the types of elements it will produce, and these elements, in turn, shape the very fabric of the universe. Stars are like cosmic foundries, forging elements from the raw materials of hydrogen and helium. Smaller stars, such as our Sun, spend the majority of their lives fusing hydrogen into helium, a process that takes billions of years. This slow, steady fusion provides the energy that powers the star and keeps it shining bright. But as these stars age and exhaust their hydrogen supply, they undergo significant transformations. They swell into red giants, expanding outward, and begin the process of fusing helium into heavier elements like carbon and oxygen. This marks the beginning of a new phase in their lives, one that gradually enriches the universe with elements that are vital to life as we know it. Massive stars, on the other hand, burn through their fuel much faster, racing through their life cycles in a fraction of the time of their smaller counterparts. As they age, they go through a series of fusion stages, creating progressively heavier elements. They can produce elements like neon, magnesium, and silicon, and continue to forge even heavier substances as they approach the end of their lives. When these massive stars reach their final stages, they collapse under their own gravity, triggering a spectacular explosion known as a supernova. This cataclysmic event releases an enormous amount of energy, creating elements that are even heavier than iron, such as gold, silver, and uranium. These heavier elements, created in the explosive death throes of massive stars, are then scattered throughout space, enriching the interstellar medium. They become part of the raw materials from which new stars, planets, and even life itself will eventually form. One of the most recent discoveries in this area has been the identification of rare elements like gold and platinum being formed during the collision of neutron stars. This process, known as the R process, occurs in the extreme conditions of a neutron star merger, where the rate of neutron capture is so high that new heavier elements are formed in a matter of seconds. The discovery of these elements in such cosmic events helps explain why gold and platinum are present on Earth. Understanding nucleosynthesis is not just about understanding where the elements come from. It's about understanding the history of the universe itself. The very atoms that make up our bodies, our planet, and everything we observe were forged in the hearts of ancient stars, long before our solar system ever came into existence. Every molecule of oxygen in the air we breathe, every carbon atom in our bodies, and every drop of water we drink has a cosmic origin. In a sense, we are all made of stardust, pieces of ancient stars that lived and died billions of years ago. This realization is one of the most profound aspects of our existence. Nucleosynthesis, the process by which elements are formed, is a vital part of the universe's ongoing life cycle. It is responsible for creating everything from the simplest elements, like hydrogen and helium, to the more complex substances we find in the periodic table today. The entire process begins in stars, which serve as the cosmic factories where the raw elements are turned into more complex ones. The chain of reactions that occurs in a star, known as stellar nucleosynthesis, gives us a glimpse into the very heart of stars, revealing how they create the elements that make up the universe around us. At the core of every star lies the process of nuclear fusion, the engine that powers the star and produces the elements we observe in the universe. Fusion begins with hydrogen atoms, the most abundant and lightest element in the universe. In stars, these hydrogen atoms collide and fuse together to form helium, releasing vast amounts of energy in the process. This process, known as hydrogen burning, occurs in two primary ways, through the proton-proton chain and the CNO cycle. In the proton-proton chain, hydrogen atoms, protons, collide and fuse to form helium, releasing energy in the form of light and heat. This is the dominant process in smaller stars, like our Sun. In larger stars, however, the CNO cycle comes into play. This process also fuses hydrogen into helium, but it uses carbon, nitrogen, and oxygen as catalysts to drive the reaction. As a star ages and its core becomes hotter and more pressured, it begins to burn heavier elements, progressing through stages of fusion that involve elements like carbon, neon, oxygen, and silicon. These reactions continue until the star reaches a point where it has fused elements all the way up to iron. Iron is a unique element in the context of nucleosynthesis. It marks the end of the line for energy-producing fusion in stars. While elements lighter than iron release energy when fused, iron requires energy to fuse. This means that once a star's core reaches iron, no further energy can be extracted from fusion, leading to the eventual collapse of the star and its subsequent explosion. But what happens to elements heavier than iron? Elements like gold, uranium, and platinum cannot be formed through the normal process of stellar fusion. Instead, they are created through a process known as neutron capture, which occurs under extreme conditions in stars. There are two primary forms of neutron capture: the S process, slow neutron capture, and the R process, rapid neutron capture. In the S process, neutrons are captured by atomic nuclei at a relatively slow rate, creating heavier elements. These elements are then ejected into space when the star dies, either through a supernova explosion or the shedding of its outer layers in a planetary nebula. The R process, however, takes place in even more extreme environments, such as during supernova explosions or the collision of neutron stars. In these violent events, the rate of neutron capture is so high that elements heavier than iron can form in a matter of seconds. This process is responsible for the creation of some of the universe's heaviest elements, including gold, uranium, and platinum. Supernova, the explosive deaths of massive stars, play a central role in the production of these heavy elements. During a supernova, the star's core collapses, triggering an immense explosion that sends a shockwave through the star's outer layers. This explosion, which releases an enormous amount of energy, is responsible for forming elements much heavier than iron. The extreme conditions in the aftermath of the explosion allow the rapid formation of gold, platinum, and other heavy elements. Neutron star mergers, too, are believed to be a significant source of heavy elements. When two neutron stars collide, they create a burst of energy that results in the creation of heavy elements, including gold and platinum, which are then released into space. This further enriches the cosmic inventory of heavy elements, which will eventually form part of new stars, planets, and life. Before stars existed, there was the Big Bang, the event that marked the birth of the universe. In those early moments, temperatures and pressures were so high that nuclear fusion could occur freely. This period, known as Big Bang nucleosynthesis, occurred within the first 3 minutes of the universe's existence. During this time, the universe was filled with a dense glowing mixture of quarks, electrons, and other particles. As the universe expanded and cooled, protons and neutrons formed, and nuclear reactions began to take place. Big Bang nucleosynthesis was responsible for the creation of some of the universe's lightest elements. hydrogen, the most abundant element, and helium, the second most abundant, were produced in large quantities. Small amounts of lithium and beryllium were also created, but these elements are much rarer. The process of Big Bang nucleosynthesis was incredibly brief, lasting only about 20 minutes before the universe cooled too much to allow further nuclear reactions to occur. By the end of this period, most of the matter in the universe was in the form of hydrogen and helium, with trace amounts of heavier elements like lithium and beryllium. The elements produced in the Big Bang laid the foundation for everything that came after. The helium created during this process continues to be produced in stars today, and much of the universe's mass is made up of the light elements created during those early moments. Understanding Big Bang nucleosynthesis gives us insight into the earliest history of the universe and how it evolved into the cosmos we see today. The ongoing processes of nucleosynthesis, whether occurring in the hearts of stars during supernova explosions or in the aftermath of neutron star collisions, have shaped the universe and everything within it. These processes not only produce the elements that make up stars and planets, but also the very atoms that constitute life itself. Without nucleosynthesis, the universe as we know it would not exist. Through these cosmic processes, we are connected to the stars and, in a profound way, to the ancient history of the universe itself. In the vast, uncharted territories of the cosmos, the elements we encounter today, carbon, oxygen, iron, and many others, are not intrinsic to the universe, but are the products of intricate cosmic processes. These elements, so fundamental to life and matter as we know it, owe their existence to a phenomenon known as nucleosynthesis. By studying the creation of elements within stars, astronomers and physicists unlock profound insights into the history and evolution of the universe itself. This process, which occurs at the very heart of stars, provides a roadmap of the cosmic journey, revealing not only the formation of stars and galaxies, but also offering clues about the nature of the processes that shaped them. The study of nucleosynthesis is integral to understanding the origins of the elements that form the building blocks of life, such as carbon and oxygen. It helps us grasp how these elements, forged in the fiery interiors of stars, have been recycled and distributed across the vast expanses of the universe. By tracing the patterns of elements across different stars and galaxies, we can gather clues about the pathways through which stars form, evolve, and eventually die, and how the very materials that make up life on Earth were dispersed across space. At the core of stellar nucleosynthesis lies a process by which stars generate new elements as they undergo various life stages. These immense celestial bodies, acting as colossal nuclear reactors, fuse lighter elements, primarily hydrogen and helium, into heavier elements like carbon, oxygen, and iron. This fusion is the star's way of generating energy, keeping it alive and shining for billions of years. As stars age, their cores grow hotter, causing the fusion process to become increasingly complex. The fusion of lighter elements continues, and heavier elements are created, slowly building up a vast array of elements essential to the fabric of the universe. One of the most significant elements produced in stellar nucleosynthesis is carbon. Carbon forms through a special process known as the triple alpha process, a crucial step in the cosmic chain that allows the formation of even heavier elements. It is this very process that enables the production of a range of elements necessary for life. Moreover, carbon plays a vital role in producing free neutrons within stars. These neutrons, once released, contribute to the S process, where iron atoms absorb neutrons and undergo nuclear transformations, evolving into even heavier elements like gold and uranium. But stars do not keep these newly created elements to themselves. As they reach the end of their life cycles, they shed mass through processes like gentle stellar winds, but particularly from lower mass stars, or through massive explosions such as supernovae in the case of larger stars. These explosive events are not only spectacular to observe, but are among the most critical sources of heavy elements in the universe. When a star explodes, particularly one much larger than our sun, it releases the newly formed elements into the surrounding space. This enriches the gas and dust that eventually coalesce into new stars, planets, and potentially life itself. The first clear evidence of stellar nucleosynthesis came when scientists discovered that the interstellar medium, the gas between stars, gradually became enriched with heavier elements over time. This revelation indicated that stars, as they formed and died, were responsible for generating these elements and spreading them across the galaxy. Furthermore, stars that formed later in the galaxy contained a higher concentration of these heavier elements compared to older stars. This discovery marked a turning point in our understanding of how the universe's chemical composition came to be. In 1952, scientists made a groundbreaking discovery when they identified technetium, a radioactive element in the atmosphere of a red giant star. Technetium has a very short lifespan, which meant it could only have been produced recently within that star. This finding provided one of the first pieces of evidence that nuclear reactions were actively occurring inside stars, confirming the process of stellar nucleosynthesis. More evidence followed with the observation of barium, another heavy element, in stars on the asymptotic giant branch, a late stage in the life of certain stars. These stars showed barium levels much higher than those found in younger stars, offering confirmation that the S process, which forms heavier elements, was taking place. Perhaps one of the most intriguing pieces of evidence for stellar nucleosynthesis comes in the form of stardust, or pre-solar grains, tiny solid particles that formed from the gases around stars. These particles, often found in meteorites, offer a direct window into the life cycle of stars. By analyzing the isotopic makeup of these grains, scientists can gain valuable insights into the chemical processes that occurred inside stars long before they perished. Stardust thus serves as a powerful tool for understanding the creation of elements in the universe. Supernovae, those cataclysmic stellar explosions, are more than just awe-inspiring cosmic events. They are crucial factories for the creation of some of the heaviest elements in the universe. The process by which elements are made in supernova is known as supernova nucleosynthesis. Within these explosive environments, temperatures and pressures are so extreme that nuclear reactions occur at an unprecedented rate. Through these reactions, elements are synthesized, particularly those between silicon and nickel on the periodic table. The rapid fusion that occurs in a supernova leads to the creation of new, heavier elements, which are then expelled into space as the star disintegrates. The formation of these elements is explained through a process called quasi-equilibrium. In simple terms, quasi-equilibrium refers to a state where nuclear reactions are nearly, but not quite, balanced. This imbalance arises due to the high concentration of silicon nuclei present during the explosion, setting the stage for the creation of new elements. This theory, proposed in the 1950s, replaced an earlier hypothesis known as the alpha process. The alpha process suggested that heavier elements were formed by repeatedly adding helium nuclei to lighter elements. However, the concept of quasi-equilibrium provided a much more accurate explanation for how elements are forged in supernovae. In addition to quasi-equilibrium, another key process in supernova nucleosynthesis is the R process, or rapid neutron capture process. The R process is responsible for creating some of the heaviest elements in the periodic table, such as uranium and thorium. It occurs when atomic nuclei rapidly capture neutrons, initiating a chain reaction of nuclear transformations. What makes the R process particularly fascinating is the speed with which it happens. It occurs so rapidly that the neutrons captured do not have time to decay before they are incorporated into the nucleus. This rapid neutron absorption leads to the formation of extremely heavy elements, many of which are crucial for the natural radioactive background of the universe. Interestingly, the R process is not dependent on the elements present in the star before it explodes. Even if a star is composed primarily of hydrogen and helium, two of the simplest elements, the R process can still occur. This is because the R process is driven by the neutron-rich environment created during the collapse of the supernova's core. As the core collapses, it produces an abundance of neutrons that fuel the process of rapid neutron capture. The fact that the R process can occur in a variety of stellar environments suggests that it is a fundamental mechanism of element creation in the universe. Astronomers have gathered compelling evidence that the R process is responsible for the formation of many of the heaviest elements we observe today. For instance, Old stars with low metallicity, meaning they contain fewer heavy elements, have been found to possess the same R process elements as younger stars. This finding suggests that these elements were created in supernovae long before the stars we observe today came into existence. The R process, therefore, not only contributes to the formation of heavy elements, but also plays a crucial role in the production of the most neutron-rich isotopes, offering a deeper understanding of the universe's elemental makeup. However, despite the progress made in understanding the R process, many questions remain unanswered. Scientists have not yet fully grasped all the details of how the R process operates within a supernova, and accurately predicting the abundance of R process elements remains a challenge. Nevertheless, the R process is an essential piece of the puzzle in understanding how the universe's most massive elements are created. Another significant process in the creation of elements in supernovae is the RP process, or rapid proton capture process. While similar to the R process, the RP process involves the rapid absorption of protons rather than neutrons to form heavier nuclei. Though theorized to play a role in the formation of proton-rich elements, the RP process is still under investigation. Its exact contribution to supernova nucleosynthesis remains uncertain, and further research is needed to clarify its role. As a supernova explodes, it releases an immense amount of energy. This release is so rapid that radioactive decay, the breakdown of unstable nuclei over time, does not significantly alter the process of element formation. Consequently, supernova nucleosynthesis can produce elements with an almost perfect balance of protons and neutrons, resulting in stable isotopes that are highly abundant in the universe. A key stage in this process is the fusion of oxygen and silicon nuclei at extremely high temperatures, forming heavier elements such as titanium, chromium, iron, and nickel. These elements, forged in the heart of a dying star, are then scattered throughout space, enriching the interstellar medium and setting the stage for the formation of new stars, planets, and even life itself. During the tumultuous life cycle of stars, not all nuclei produced through their various processes remain stable. Some, in fact, are inherently radioactive, a trait that leads them to decay into other elements over time. This phenomenon is particularly evident in supernova explosions, where the conditions are extreme, and the creation of isotopes is abundant yet short-lived. Elements such as titanium-44, Ti-44, chromium-48, Cr-48, iron-52, Fe-52, and nickel-56, Ni-56 are produced in large quantities during these explosive events. However, these isotopes are radioactive, and they gradually decay into more stable forms. For example, titanium-44 decays into stable titanium-48, chromium-48 transforms into stable chromium-52, and iron-56 remains stable as it is. What makes supernova explosions particularly captivating is their role in nuclear synthesis, a process responsible for the formation of new elements under extreme conditions. Among the most fascinating products of these explosions are gamma rays, high-energy photons emitted during the decay of radioactive isotopes. These gamma rays hold immense scientific value, as they provide a crucial tool for astronomers to observe and understand the processes occurring within the heart of a supernova. The radiation emitted during these decays can be detected by instruments in space, allowing scientists to gather vital data about the explosion's dynamics. One of the pivotal moments in the study of supernova nuclear synthesis came in 1987, when astronomers observed a supernova explosion, aptly named Supernova 1987A. This event became a cornerstone in the field of gamma-ray astronomy, as it offered the first concrete confirmation of explosive nucleosynthesis. Gamma-ray emissions originating from the explosion allowed scientists to identify the specific isotopes involved, particularly cobalt-56, Co-56, and cobalt-57, Co-57. These isotopes were formed through the decay of radioactive cobalt, and their relatively short half-lives, lasting no more than about a year, provided compelling evidence that these elements had indeed been produced during the explosion itself. What makes this discovery even more remarkable is the fact that the detection of gamma rays from supernovae was not a new concept. In fact, scientists had predicted back in 1969 that gamma rays emitted during supernova explosions would offer a crucial means of observing and confirming nucleosynthesis. This foresight was instrumental in shaping the development of NASA's Compton Gamma Ray Observatory, which was specifically designed to detect such high-energy radiation. In addition to gamma-ray observations, another significant line of evidence for supernova nucleosynthesis has been found in tiny grains of stardust, microscopic particles that form in the cooling and expanding remnants of a supernova explosion. As these grains cool, they trap isotopic signatures specific to the elements synthesized during the explosion. These tiny grains have provided scientists with invaluable insight into the processes that took place within the star before it exploded, offering a snapshot of the early stages of nucleosynthesis in the universe. One of the most exciting discoveries in this realm is the identification of radioactive titanium-44 in stardust grains. The high abundance of Ti-44 found in supernova stardust confirmed predictions made as early as the 1970s about the existence of these grains, now known as pre-solar grains. These grains offer a rare and detailed glimpse into the chemical processes that occurred in the star prior to its catastrophic demise. Recently, the study of neutron-star mergers has opened a new chapter in our understanding of how the heaviest elements in the universe are formed. Neutron stars, the dense remnants of massive stars that have gone supernova, contain an abundance of neutrons, which are crucial in the formation of heavy elements. For years, scientists had speculated that when two neutron stars collide, they could produce vast amounts of heavy elements, but definitive evidence had been elusive. That was until 2017, when a groundbreaking event designated GW170817 allowed multiple scientific organizations, such as LIGO, Virgo, and the Fermi Gamma Ray Space Telescope, to observe both gravitational waves and electromagnetic signals from a neutron-star merger. This momentous discovery marked the first direct evidence of a neutron-star collision, and it revealed the presence of heavy elements like gold in the aftermath of the merger. The process behind the formation of these heavy elements is equally fascinating. When two neutron stars merge, their ultra-dense matter begins to decay and cool down, triggering the synthesis of elements such as gold, platinum, and uranium. While neutron star mergers have now been identified as one of the primary sources of these elements, a further discovery in 2021 provided another crucial piece to the puzzle. This time, astronomers detected the first ever neutron star black hole merger, NSBH, offering yet another clue about the processes responsible for creating the universe's heaviest elements. However, most research still suggests that binary neutron star BNS mergers are the most likely culprits in the formation of heavy metals. In addition to neutron star mergers, nucleosynthesis also takes place in the accretion disks surrounding black holes. These rotating disks of matter, which form as material spirals into the black hole's intense gravitational field, can generate a variety of elements through the extreme heat and pressure that occur in these environments. While black holes themselves remain enigmatic and largely inaccessible to direct observation, the accretion disks around them provide fertile ground for the creation of new elements. Another intriguing phenomenon contributing to element formation is cosmic ray spallation. This process occurs when fast-moving cosmic rays, primarily protons, collide with interstellar matter, breaking it apart and producing lighter elements. Some of the elements created through cosmic ray spallation include lithium, beryllium, and boron, all of which are essential building blocks of matter in the universe. This process also accounts for much of the helium-3 found in space, although some of it may have been formed during the Big Bang. As cosmic rays bombard atomic nuclei, they fragment carbon, nitrogen, and oxygen into lighter elements. Despite its significance, cosmic ray spallation does not contribute significantly to the production of hydrogen or helium, as these elements already existed in vast quantities since the early moments of the universe. Cosmic ray spallation also plays a crucial role in the creation of certain isotopes, such as carbon-14, which is used in radiocarbon dating, allowing scientists to date ancient objects and gain insight into the past. The process occurs primarily when cosmic rays strike nitrogen-14 in Earth's atmosphere, transforming it into carbon-14. Other isotopes like iodine-129 are also produced in this way, helping scientists trace the origins of ancient cosmic events. In addition to natural processes like radioactive decay and cosmic ray spallation, human-made processes also contribute to the creation of elements. In laboratories, scientists can artificially produce nuclides, unstable isotopes of elements such as technetium. While these artificial nuclides are useful for research, most of the nuclides found on Earth are the product of natural processes. These nuclides play a pivotal role in helping scientists understand geological events, date rocks, and track the ongoing cycles of nature. For instance, radioactive decay is one of the key mechanisms through which nuclides are formed. When large, unstable atomic nuclei decay, they release smaller particles known as radiogenic daughter nuclides. Over millions of years, the decay of elements like uranium-235 and uranium-238 produces a range of intermediate nuclides, which eventually decay into stable elements like lead. Similarly, the decay of potassium-40 in Earth's crust results in the formation of argon-40, an important component of Earth's atmosphere. Helium is also produced in small quantities through alpha decay, a process where a nucleus releases a helium atom. Another important process is spontaneous fission, which occurs when the nucleus of a heavy atom splits into two smaller fragments, releasing energy and creating new nuclides. Elements like thorium-232, uranium-235, and uranium-238 all undergo spontaneous fission, leading to the formation of elements such as technetium and promethium. These processes of nuclear decay and fission contribute significantly to the ongoing creation of elements, both in stars and on Earth. The study of nucleogenic processes, those resulting from nuclear reactions, has further expanded our understanding of element formation. Neutrons, often produced during spontaneous fission, can collide with other nuclei, causing them to transform into new elements. This process is a crucial component of the ongoing production of many elements found on Earth, such as neon-21 and neon-22. Cosmogenic nuclear synthesis, the creation of elements through cosmic rays, further adds to the complexity of element formation. When cosmic rays interact with Earth's atmosphere, they create new isotopes, offering yet another window into the intricate processes that govern the universe's composition. For example, cosmic rays transform nitrogen-14 into carbon-14, which is essential for dating ancient materials. Other isotopes, such as iodine-129, are similarly formed, contributing to our ability to understand the history of both the Earth and the cosmos. These various processes of nucleosynthesis, both cosmic and nuclear, continue to captivate scientists as they help unravel the mysteries of how the elements that make up our world and our universe were created. From the explosive death of stars to the collision of neutron stars, from the subtle influence of cosmic rays to the artificial creation of elements in laboratories, the story of element formation is one of profound interconnectedness, revealing the vast, complex processes that govern the cosmos and our own planet. Through the study of these phenomena, we gain not only insight into the origins of the elements, but also a deeper understanding of the fundamental workings of the universe itself. In the very early moments following the Big Bang, the universe underwent a transformative phase, a rapid expansion that reshaped everything we know today. This theory, known as cosmic inflation, suggests that during these first fractions of a second, the universe expanded at an astonishingly fast pace, much quicker than anything we could possibly imagine. To put it into perspective, the entire observable universe expanded from something no larger than a grain of sand in mere moments. This dramatic growth laid the groundwork for everything that followed, from galaxies to stars, planets, and eventually life itself. But this extraordinary expansion didn't just happen spontaneously. It was driven by a delicate interplay of forces, each playing a crucial role in the unfolding of the cosmos. Gravity, quantum mechanics, and the energy fields present in those early moments were all part of this intricate process. These forces didn't just shape the universe's expansion, they set the stage for the highly structured universe we observe today. Before we dive deeper into the mechanics of cosmic inflation, it's important to understand the Big Bang itself. Contrary to popular belief, the Big Bang wasn't a conventional explosion. Rather, it was a moment in time when the universe began expanding from a hot, dense, and infinitely small point. Every particle, every bit of matter was packed into this tiny space, And as the universe began to stretch outward, it started its journey toward becoming the vast and complex structure we see today. Yet the Big Bang theory on its own has a significant gap in explaining the universe as we see it. Specifically, it doesn't explain why the universe is so uniform. When we look out into space, we notice that the universe appears almost identical in all directions. Galaxies, stars, and cosmic structures are spread in a consistent, almost predictable way. But how did this uniformity come about, especially considering the chaotic and unstable conditions of the early universe? This is where the theory of cosmic inflation becomes essential. Proposed in the early 1980s by physicist Alan Guth, cosmic inflation addresses this question directly. Guth's idea suggested that in the first moments of the universe's existence, it expanded at a rate far exceeding the speed of light. The analogy goes like this. Imagine a tiny grain of sand stretching to the size of the entire observable universe in the blink of an eye. This unfathomable rate of expansion didn't just stretch space, it smoothed out the chaotic irregularities of the early universe, creating the uniformity we observe in the cosmos today. Moreover, it helps explain why distant galaxies are so far apart, as well as why the universe looks essentially the same from every direction. Central to the theory of cosmic inflation are several fundamental forces, each contributing to this rapid expansion. Among these, gravity, quantum mechanics, and the hypothetical inflaton field played crucial roles. Let's break them down. Gravity, the force that keeps us grounded on Earth and governs the motion of planets and stars, also played a pivotal role during inflation. In the early universe, gravity was weak compared to the forces driving inflation. However, after inflation ended, gravity became the dominant force, causing matter to clump together and form stars, galaxies, and other structures. Quantum mechanics. At the microscopic scale, particles behave in ways that defy our everyday understanding. The principles of quantum mechanics govern the behavior of the smallest building blocks of the universe: atoms, electrons, and photons. In the context of inflation, quantum fluctuations in the inflaton field were crucial. These fluctuations created tiny variations in the density of the universe, and over time, these variations grew, eventually leading to the formation of galaxies, clusters of galaxies, and other large-scale structures. The inflaton field. The inflaton field is a theoretical energy field that is thought to have driven the rapid expansion of the universe during inflation. Essentially, the inflaton field acted like a form of energy that caused space itself to stretch exponentially. When the energy from the inflaton field was exhausted, the universe transitioned into a slower, more gradual phase of expansion, known as reheating. This marked the beginning of the universe's more familiar structure. Once the inflationary period ended, the universe was no longer expanding at the same extreme rate. However, the effects of this rapid expansion were still very much present. The tiny quantum fluctuations that occurred during inflation set the stage for the universe's current structure. They created small differences in the density of matter and energy, which would later become the seeds for galaxies and stars. Over billions of years, gravity acted on these differences, causing matter to clump together and form the stars, galaxies, and galaxy clusters that populate the universe today. In a way, the universe we see around us is a direct result of the patterns established during inflation. One of the most fascinating aspects of cosmic inflation is the way multiple forces came together to produce the universe we know. It wasn't just one force driving the rapid expansion. It was a combination of gravity, quantum mechanics, and the inflaton field that created the right conditions. This balance of forces is what made inflation possible. If the force driving inflation had been too weak, the universe wouldn't have expanded fast enough to smooth out the irregularities we see today. On the other hand, if inflation had been too powerful, the universe could have expanded too rapidly, preventing the formation of galaxies and stars altogether. These fluctuations in the early universe also laid the groundwork for the formation of the large-scale structure of the universe. These density variations gave rise to what is often referred to as the cosmic web, a vast network of galaxies and galaxy clusters stretching across the entire universe. The structure of the universe we see today can be traced back to the inflationary period, and the seeds of today's galaxies were planted during this time. Cosmic inflation has profound implications for how we understand the universe. It suggests that the universe wasn't born from a singular event or explosion, but rather from a highly complex, finely tuned process that involved multiple forces working in concert. The universe's current structure, including the distribution of galaxies, the cosmic microwave background radiation, and even the behavior of distant galaxies, can all be traced back to this period of rapid expansion. One of the most mysterious components of this theory is the concept of dark matter, a strange and invisible substance that seems to exist in vast quantities throughout the universe. While we can't see dark matter directly, its presence is inferred from the gravitational effects it has on visible matter. This invisible matter influences how galaxies form, bend light through gravitational lensing, and even affects the movement of galaxies within clusters. In the widely accepted lambda cold dark matter, lambda CDM, model of the universe, dark matter makes up about 26.8% of the universe's total mass energy content, while regular matter, the stuff we can see, makes up just 5%. A staggering 68.2% of the universe consists of dark energy, a mysterious force driving the accelerated expansion of the universe. Together, dark matter and dark energy make up around 95% of the universe's total energy. Yet, we still don't fully understand what dark matter is. It doesn't interact with light or any other form of radiation, which makes it nearly impossible to detect using conventional methods. Several theories have been proposed to explain dark matter. One possibility is that it consists of tiny particles like WIMPs, weakly interacting massive particles, or axions, which barely interact with normal matter. Another possibility is that dark matter could be composed of ancient black holes, remnants from the early universe. Most scientists believe that dark matter is cold, meaning its particles move slowly, allowing them to accumulate and form structures over time. However, some scientists still question the nature of dark matter, proposing alternative theories, such as modified gravity models. These alternative theories suggest that our understanding of gravity may need to be adjusted, but no current model can fully account for all the observed phenomena, implying that dark matter is likely a key piece of the cosmic puzzle. The history of dark matter is a rich and fascinating one, full of significant discoveries and theories that have gradually led to our current understanding of the universe. In the late 19th century, Lord Kelvin made a critical observation about the movement of stars in our solar neighborhood, suggesting that invisible matter might be influencing the motion of stars. This idea would form the early foundation for what would later be recognized as dark matter. As the decades passed, scientists like Jan Oort and Vera Rubin built upon this idea, using the motion of stars and galaxies to suggest that the visible universe wasn't the full picture. By the mid-20th century, it became clear that something was missing. Something invisible was exerting a profound gravitational influence on the observable universe. Despite the challenges and unanswered questions, the concept of dark matter remains one of the most compelling mysteries in modern cosmology, and it's an essential part of the story of cosmic inflation, the process that shaped the universe into the vast structured entity we observe today. In the early 20th century, as astronomers turned their gaze to the heavens, they began noticing curious anomalies that would later challenge fundamental assumptions about the universe. One of the most profound of these came in 1933 when Swiss astrophysicist Fritz Zwicky, working at the California Institute of Technology, made a groundbreaking discovery while studying galaxy clusters. He was observing the Coma cluster, a massive collection of galaxies, when he observed something deeply puzzling. The galaxies within the cluster were moving much faster than anyone had anticipated, given the visible mass of the cluster. This discrepancy, Zwicky proposed, indicated the presence of an unseen force. He suggested that there was a large amount of invisible mass pulling the galaxies together through gravitational attraction, a mass he referred to as dunkel materie, or dark matter. Zwicky estimated that the Coma cluster contained roughly 400 times more mass than could be seen with telescopes, based on the galaxy's high velocities. His revolutionary idea was that this invisible mass was responsible for the gravitational pull that held the galaxies together. However, Zwicky's estimates were far from accurate, largely due to outdated values for the cluster's size and distance. Despite these miscalculations, he was among the first to propose the existence of invisible mass in the universe, something that could exert gravitational forces yet was undetectable by conventional means. This insight, while premature, set the stage for future breakthroughs in understanding dark matter. Zwicky, however, did not envision dark matter the way we do today. He thought of it merely as ordinary matter that didn't emit light, perhaps dust or gas too faint to detect with telescopes, rather than the mysterious exotic material we now associate with the term. Still, his work marked a significant step forward, laying the foundation for decades of exploration into what would later become one of the biggest mysteries in astrophysics. As the years passed, more evidence began to surface, strengthening the idea that dark matter might be a crucial component of the universe. In 1939, astronomer H.W. Babcock made an important observation that further hinted at the existence of unseen matter. Babcock was studying the Andromeda Galaxy, the nearest large spiral galaxy to our own Milky Way, and noticed that the stars on the outer edges of the galaxy were moving much faster than expected. If only the visible matter in the galaxy was taken into account, the stars at the outskirts should be moving much more slowly. This discrepancy suggested that there was far more mass in the galaxy than could be accounted for by its visible stars alone. At first, Babcock speculated that this strange motion could be due to light being absorbed by the galaxy, or perhaps some unknown physical mechanism at play in its outer regions. But his findings, which indicated that something invisible was influencing the galaxy's motion, provided an early clue that galaxies might contain hidden mass. This idea would take several more decades to gain widespread acceptance, but Babcock's observations were crucial in the gradual accumulation of evidence for dark matter. The following year, in 1940, another astronomer, Jan Oort, made a pivotal discovery while studying the galaxy NGC 31115. Oort found evidence of a large, invisible halo of mass surrounding the galaxy, yet another indication that galaxies might be enveloped in vast quantities of unseen matter. As astronomers continued to examine galaxy clusters and the motion of galaxies within them, the notion of dark matter began to take hold in the scientific community. By the 1970s, the idea of dark matter had gained serious traction. Multiple scientific discoveries in that decade helped to solidify its theoretical framework. In 1974, two independent research groups, one led by Jeremiah Ostriker, Jim Peebles, and Amos Yehiel in Princeton, New Jersey, and another led by John Anastos and Anastasios Kasik in Tartu, Estonia, arrived at the same conclusion. Both groups found evidence suggesting that galaxies were surrounded by enormous halos of invisible matter. This reinforced the idea that galaxies contained far more mass than could be observed with optical telescopes. One of the key observations pointing to the existence of these invisible halos came from studying the rotation of galaxies. Vera Rubin and Kent Ford, using new spectrographs, were able to measure the speeds of stars in the outer parts of galaxies with greater accuracy. Their data revealed a surprising pattern. The stars at the outer edges of galaxies were rotating at much higher speeds than expected. Based on the mass visible in the form of stars, the rotation curve should have fallen off gradually, as described by Kepler's laws of motion. However, the curves remained unexpectedly flat, even in the outermost regions of the galaxies. This discrepancy strongly suggested the presence of additional mass, dark matter, that was exerting gravitational influence on the galaxies. At the same time, radio astronomers were making new strides in their understanding of galaxies. Using advanced radio telescopes to observe hydrogen gas in galaxies, astronomers were able to measure the rotation curves at even greater distances than was possible with optical observations. Hydrogen gas, unlike starlight, extends much farther from the center of a galaxy and is visible even in the outskirts. This allowed astronomers to get a clearer picture of the total mass in a galaxy. Early radio studies of the Andromeda Galaxy using powerful telescopes like the Green Bank Telescope and the Jodrell Bank Dish showed that the hydrogen gas was moving in ways that defied expectations, according to Kepler's laws. These results added weight to the hypothesis that galaxies contained invisible halos of dark matter. The observations became even more compelling in the mid-1970s. In 1975, astronomers Roberts and Whitehurst were able to measure the rotation speeds of stars in the Andromeda galaxy all the way out to 30 kiloparsecs, about 100,000 light-years from the galaxy's center. Their data revealed that the galaxy's rotation curve remained flat at these extreme distances, suggesting that the galaxy contained far more mass than could be accounted for by its visible stars alone. This was a clear indication that there was more mass extending far beyond the galaxy's visible boundaries, supporting the idea of an invisible dark matter halo. With improved technology and more precise measurements, the 1970s and 1980s brought further confirmation of the existence of dark matter. Radio telescopes, used in interferometric arrays where multiple radio telescopes work together, allowed astronomers to map the hydrogen gas in distant galaxies more accurately. In 1972, researchers Rogstad and Shostak studied the hydrogen rotation curves of 5 spiral galaxies and found that all of them displayed flat curves, suggesting the presence of invisible mass beyond the observable stars and light. By the late 1970s, the idea that dark matter halos were likely encircling galaxies was widely accepted in the scientific community. The 1980s and 1990s saw further advancements in our understanding of dark matter. Studies in 1996, led by astronomers Persic, Salucci, and Stell, examined nearly 1,000 spiral galaxies and found strong evidence supporting the presence of dark matter. Other lines of evidence, including the strange phenomenon of gravitational lensing, in which galaxy clusters bend light from objects behind them, and the spread of hot gas in galaxies, also hinted at the existence of invisible mass. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, revealed tiny temperature fluctuations or anisotropies that could only be explained by the presence of dark matter. Today, most scientists agree that dark matter is composed of particles that have yet to be discovered. These particles, whatever they may be, do not interact with light in the same way that normal matter does. Their exact nature remains one of the most tantalizing questions in modern physics. The search for dark matter particles has become one of the most important quests in astrophysics, with researchers around the world employing a wide variety of methods and experiments to uncover their identity. In simple terms, when scientists discuss matter in the universe, they are referring to anything that contributes to the overall energy and density of the cosmos. As the universe expands, this matter decreases in density, following a specific rule. It decreases as the cube of the expansion. This is different from radiation, which decreases even faster as the universe grows, following an inverse relationship to the fourth power of expansion. The cosmological constant, however, behaves in a unique way. It remains constant regardless of the expansion of the universe, meaning its energy density does not change as the universe stretches. This difference in the behavior of matter, radiation, and the cosmological constant is related to a phenomenon called radiation redshift. To picture this, imagine the universe expanding. If the observable universe's size doubles, the scale factor of expansion also doubles. As a result, the energy of phenomena like the cosmic microwave background radiation weakens because each photon or light particle is stretched over a larger area, reducing its energy. This same effect occurs with ultra-relativistic particles, like early neutrinos. However, the cosmological constant, a property of space itself, does not change, no matter how much the universe grows. As for dark matter, it refers to parts of the universe that we cannot directly observe, but that still exert mass and gravitational effects, obeying similar laws to regular matter. The journey to understanding dark matter is far from over, but the groundwork laid by scientists like Zwicky, Babcock, Rubin, and many others has propelled us into an era where we now understand that most of the mass in the universe remains hidden from view, awaiting the day when we can finally glimpse it. Dark matter, often described in scientific circles as a mysterious and invisible substance, stands apart from the familiar types of matter we encounter in everyday life. Unlike the ordinary particles that make up stars, planets, and the air we breathe, dark matter is not composed of the usual atomic particles. Instead, it remains undetectable by the usual means we use to observe ordinary matter, such as light or electromagnetic radiation. Its existence is inferred not by direct observation, but by its gravitational effects on visible matter. One interesting exception to this invisibility is the concept of missing baryons, which refers to particles that are unaccounted for in the standard model, but still have mass. The concept of dark matter is deeply linked to the structure and behavior of galaxies, especially the iconic spiral galaxies we observe in the universe. These galaxies, with their arms spiraling outward from a central core, have a peculiar way of rotating that has baffled astronomers for decades. As you move away from the center of a spiral galaxy, the visible mass density of the galaxy decreases. If all of the galaxy's mass were visible, its behavior would resemble the workings of a simple system, much like how planets orbit the sun in our solar system. Kepler's third law of planetary motion dictates that objects farther from the center of a gravitational field should move more slowly. Planets on the outer edges of the solar system move slower than those closer to the sun. However, in spiral galaxies, the rotation speeds of stars and gas do not slow down as expected. Instead, they either remain constant or even accelerate the farther out they are from the center. This anomaly presents a significant puzzle. If only visible matter were present, the observed patterns of rotation would not be possible. Instead, astronomers believe that large amounts of invisible, non-luminous matter, dark matter, must be located in the outer regions of galaxies, exerting its gravitational influence on the stars and gas within. In bound systems like galaxies, the motion of stars is further explained by a rule known as the virial theorem. This principle helps astronomers understand how mass is distributed across a system by examining the speeds at which stars move. Yet, when astronomers apply this theorem to galaxy clusters, elliptical galaxies, and dense star clusters, they often encounter a troubling mismatch. The measured speeds of stars do not correspond to the amount of visible mass present. Even accounting for complex orbital patterns of stars, this discrepancy suggests that invisible matter is influencing the dynamics of these systems, again pointing to the elusive presence of dark matter. A key method for studying dark matter involves galaxy clusters, which act as cosmic laboratories for understanding this mysterious substance. These clusters allow scientists to measure mass in three different ways: by analyzing the speeds at which galaxies within the cluster are moving, by studying the X-rays emitted by the hot gas present within the cluster, and by observing the phenomenon of gravitational lensing. Each of these methods provides independent evidence for the existence of dark matter. In particular, gravitational lensing, the bending of light caused by massive objects, has proven invaluable. By analyzing the distortions in light caused by the presence of massive clusters, astronomers can estimate the mass of these clusters without directly observing the galaxies themselves. In the case of galaxy clusters, these methods consistently point to a surprising conclusion. Dark matter accounts for roughly 5 times the mass of all the visible matter within these clusters. The discovery of this invisible substance has revolutionized our understanding of the universe, offering profound insights into the nature of cosmic mass and structure. One particularly fascinating aspect of dark matter involves its connection to the theory of general relativity. This theory predicts a phenomenon known as gravitational lensing, which occurs when massive objects like galaxies or groups of galaxies sit between an observer and a distant light source. These massive objects act as cosmic lenses, bending and distorting the light that passes through them. The greater the mass of an object, the more it bends the light. This distortion can cause the light from distant objects, such as quasars, to appear warped or magnified. Gravitational lensing comes in 2 primary forms: strong and weak lensing. Strong lensing occurs when the light from a background object, such as a distant galaxy, is bent so dramatically that it forms arc-like shapes in the sky. By studying these arcs, scientists can infer the mass of the intervening galaxy cluster, causing the lensing effect. Weak lensing, on the other hand, results in much subtler distortions in the shapes of galaxies, which are harder to detect, but still reveal valuable information about the distribution of mass in the universe. Both forms of lensing provide key insights into the distribution of dark matter in galaxy clusters, with weak lensing offering a more precise view of its spread throughout the universe. This ability to observe dark matter indirectly through its gravitational effects underscores a critical distinction between dark matter and regular matter. While ordinary matter interacts strongly with light, absorbing, emitting, and scattering it, dark matter does not interact with light at all. Instead, its influence is felt through gravity, both on smaller scales, such as in the motion of stars within galaxies, and on larger scales, such as its influence on the cosmic microwave background, CMB, a faint glow left over from the Big Bang. The CMB, although close to a perfect blackbody radiation spectrum, contains small variations in temperature and isotropies that provide a wealth of information about the early universe. These minute temperature fluctuations, about 1 part in 100,000, offer clues about the distribution of matter in the early universe. In 1992, the COBE satellite made the first detection of these anisotropies, and subsequent missions like the Boomerang experiment, the WMAP satellite, and the Planck spacecraft have provided increasingly detailed maps of these variations. By analyzing the angular power spectrum of the CMB, essentially a graph that plots the distribution of these temperature fluctuations, scientists can uncover details about the universe's age, composition, and structure. The peaks and valleys in the angular power spectrum correspond to key features of cosmological theory, and comparing these patterns with theoretical models allows scientists to refine their understanding of dark matter and its role in the formation of the universe. In the early universe, the cosmos was a nearly uniform expanse, with only tiny fluctuations in density. Over time, these fluctuations began to grow and collapse under their own gravity, forming the first stars and galaxies. The presence of dark matter played a crucial role in this process. While regular matter interacted strongly with radiation and was slowed in its ability to clump together, dark matter, being unaffected by radiation, was free to collapse under its own gravity. This allowed dark matter to form the first gravitational wells, which in turn attracted regular matter, speeding up the formation of galaxies and larger cosmic structures. A dramatic example of dark matter's influence is seen in the Bullet Cluster, a pair of colliding galaxy clusters. This collision has provided a unique opportunity to study the behavior of dark matter, as the gravitational lensing observed in the region reveals a surprising separation between the visible matter and the mass detected by the lensing effect. The visible matter, made up of gas and galaxies, is displaced from the dark matter, which remains unaffected by the collision. This discrepancy is difficult to explain with traditional models of gravity, but it aligns perfectly with the predictions of dark matter theory, further cementing its role in shaping the structure of the universe. Through these various observations and experiments, dark matter continues to emerge as a key player in the evolution of the cosmos. Although we cannot yet detect it directly, its effects on visible matter and its presence in the universe's largest structures provide compelling evidence that dark matter is a fundamental component of the universe's fabric, an invisible force shaping the cosmos in ways we are only beginning to understand. In the ongoing quest to understand the vast and enigmatic universe, one of the most intriguing puzzles is dark matter. While the standard theory of dark matter offers a relatively simple explanation for many phenomena, there are still vast unknowns. When two massive galaxy clusters collide, the visible gas within them interacts with light and other forms of radiation. During this dramatic event, the gas is slowed down and cooled by electromagnetic forces. However, dark matter, which does not interact with light in the same manner, passes through the collision unaffected, continuing its journey through the cosmos. This results in the separation of the dark matter from the visible gas, creating two distinct peaks in gravitational lensing patterns that we can observe. In addition to dark matter, astronomers have relied on other methods to probe the mysteries of the universe. One of these is the use of Type 2a supernovae as standard candles. These are exploding stars that, despite their violent nature, have a predictable luminosity. By measuring their apparent dimness, scientists can determine their distance from Earth, giving us a reliable gauge to measure vast cosmic distances. This technique has revealed an astonishing and unsettling truth. The universe is expanding at an ever-accelerating rate. This accelerated expansion is often attributed to a mysterious force known as dark energy. Another important piece of the puzzle comes from studying baryon acoustic oscillations, or BAO, which are fluctuations in the density of normal matter, known as baryons, that occurred on a large scale in the early universe. These fluctuations were generated by sound waves propagating through the hot, dense mixture of photons and baryons that existed before atoms had formed. As the universe cooled, these waves left behind subtle imprints that we can still detect today in the cosmic microwave background, CMB radiation. Over time, dark matter and normal matter began to clump together, but the original fluctuations in density have persisted, even though their effect has diminished. In fact, galaxies are still found to exhibit a slight tendency to be separated by approximately 147 million light-years, a remnant of these early oscillations. This pattern was predicted in the 1990s and confirmed in 2005 by large-scale galaxy surveys, including the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining these measurements with CMB observations, scientists can estimate key cosmic values, such as the rate of expansion of the universe and the total amount of matter it contains. These results are consistent with the lambda cold dark matter, lambda CDM model, which remains the prevailing theory of cosmology. However, creating an accurate three-dimensional map of the universe remains a complex challenge. Large surveys of galaxy redshifts are crucial for constructing these maps, but they are not without their limitations. Redshift, the phenomenon where light stretches as it travels across the expanding universe, can be distorted by several factors. The most significant of these is the universe's overall expansion, but there's also a smaller influence from the motion of the galaxies themselves, known as peculiar velocity. In general, superclusters of galaxies, massive collections of galaxies bound together by gravity, are expanding at a slower rate than the average cosmic expansion because their gravity is pulling matter together. On the other hand, voids, vast, empty regions between clusters, expand faster than the universe as a whole. This differential expansion creates a fascinating set of observational effects. For example, galaxies in front of a supercluster will appear to move toward it more quickly than expected, which results in a higher redshift. Conversely, galaxies behind a supercluster appear to have a slightly lower redshift than anticipated. This phenomenon causes superclusters to appear flattened along our line of sight, while voids appear stretched. While this effect is subtle and difficult to discern in a single structure, it becomes more apparent when scientists average data from many galaxies across the universe. This was first predicted by astrophysicist Nick Kaiser in 1987 and confirmed in 2001 through the 2DF Galaxy Redshift Survey, with results that align with predictions from the lambda CDM model. In a related area of study, the Lyman alpha forest plays an essential role in advancing our understanding of cosmology. The Lyman alpha forest refers to the collection of absorption lines in the spectra of distant galaxies and quasars. These lines are the result of neutral hydrogen absorbing light at a specific wavelength known as the Lyman alpha transition. By analyzing the Lyman alpha forest, astronomers can refine their cosmological models, often corroborating the findings from other methods like the WMAP, Wilkinson microwave anisotropy probe data. Dark matter itself is often categorized into three distinct types: cold, warm, and hot. These names do not refer to the literal temperature of the particles, but instead to how fast they moved in the early universe. The fundamental concept here is the free streaming length, FSL, which refers to how far a particle could travel due to random motion before the universe expanded too much for it to move further. The type of dark matter is determined by comparing the FSL to the size of a proto-galaxy, the early structure that would eventually evolve into a full-fledged galaxy. If the FSL is much smaller than the size of a proto-galaxy, the matter is classified as cold dark matter. If the FSL is about the same size as the proto-galaxy, it's classified as warm dark matter. And if the FSL is much larger, it's considered hot dark matter. Some theories suggest a mixture of these types, a hypothesis that was more popular in the mid-1990s, but became less favored after the discovery of dark energy. The key idea here is that the expansion of the universe itself created a limit to how far particles could travel. Faster-moving particles, like those in hot dark matter, could travel farther before the universe expanded too much. Slower-moving particles, like those in cold dark matter, couldn't move as far. This differential movement has profound implications for the formation of structures in the early universe. Hot dark matter would have led to the creation of large, diffuse structures like superclusters. These structures would eventually break apart into smaller galaxies. In contrast, cold dark matter allowed for the formation of smaller structures first, galaxies that would later group together to form clusters and superclusters. Recent deep field images of the universe confirm that galaxies were among the first structures to form, followed by clusters and superclusters. This supports the theory that most dark matter is cold rather than hot. This distinction is crucial because it helps explain why neutrinos, which move nearly at the speed of light and would be considered hot dark matter, cannot account for most of the dark matter in the universe. Dark matter itself remains elusive, yet its influence on the structure of the universe is undeniable. In fact, dark matter is defined by the way it interacts with normal, visible matter, mainly through gravity. This means that dark matter might not be composed of a completely new kind of particle, but rather could consist of regular, familiar matter like protons or neutrons. Many objects that astronomers already know well, such as planets, brown dwarfs, red dwarfs, white dwarfs, neutron stars, and black holes, could fall into this category. These hard-to-detect objects are collectively known as MACOs, massive compact halo objects. For a time, scientists speculated that MACOs made up the majority of dark matter, but this theory has since been largely rejected. Strong evidence now suggests that most dark matter is not composed of regular, visible matter. One of the key reasons is that if enough ordinary matter, such as gas or dust, existed in the universe, we would be able to detect it, especially when it's illuminated by the light of stars. However, no such matter is seen in the quantities we would expect. Furthermore, the Big Bang Theory helps explain the creation of the elements we observe today. According to the theory, if there had been more regular matter, called baryons, in the early universe, we would have observed a higher abundance of elements like helium and lithium. Yet, the observed abundance of these elements is consistent with the amount of normal matter that we see today, only about 4 to 5% of the universe's total mass. Thus, while dark matter continues to remain one of the universe's greatest mysteries, the evidence overwhelmingly supports the notion that it plays a crucial role in shaping the cosmic structure we observe, influencing everything from galaxy formation to the expansion of the universe itself. The search for dark matter is ongoing, but each new discovery brings us one step closer to unlocking the secrets of the cosmos. The vast and mysterious world of dark matter has been one of the most intriguing puzzles in modern cosmology, and though significant progress has been made in our understanding, the complete nature of dark matter remains elusive. Large-scale studies of galaxies and other cosmic structures have shown that the total amount of matter in the universe is only about 30% of what is needed to keep the universe stable. This discrepancy has sparked a deeper investigation into the unseen forces shaping the cosmos. What is this missing matter, this invisible substance that seems to govern the movements of galaxies and stars? Further research has revealed that a small portion of this mysterious matter is composed of regular hidden objects, like small planets or black holes. These objects, known as MACOs, massive compact halo objects, have been identified through a technique called gravitational microlensing, which involves the bending of light by gravity. However, studies indicate that MACOs alone cannot account for the majority of dark matter. Their masses fall within a range that excludes nearly all plausible candidates for dark matter, suggesting that something more exotic is at play. Detailed studies of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang, have provided strong evidence for the existence of a different form of matter. Missions like WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have mapped the CMB with unprecedented precision, revealing that about 56% of the universe's total matter doesn't interact significantly with light or ordinary matter except through gravity. This suggests that dark matter is largely invisible, detectable only by the gravitational influence it exerts on visible matter. In other words, dark matter exists in the shadows, its presence only revealed through its gravitational effects on stars, galaxies, and clusters of galaxies. This raises a fundamental question. If regular matter, known as baryonic matter, doesn't account for most of dark matter, what exactly is it made of? The leading hypothesis points to a type of non-baryonic matter that doesn't interact with light in the way ordinary matter does. There are two primary candidates for this invisible matter: new, mysterious particles and primordial black holes left over from the early universe. These non-baryonic particles are theorized to have been created during the Big Bang, but do not participate in the creation of elements in the early universe, a process known as Big Bang nucleosynthesis. Instead, they only reveal themselves through their gravitational influence, bending light in ways that scientists can detect, a phenomenon known as weak lensing. Some types of dark matter are even believed to interact with themselves or with normal particles. This self-interaction could produce detectable signs such as gamma rays or neutrinos, which scientists might be able to observe indirectly. Among the most widely studied dark matter candidates are weakly interacting massive particles, WIMPs. While WIMPs don't have a strict definition, they are generally thought to be elementary particles that interact through gravity and possibly other weak forces, like the weak nuclear force. Theoretical models suggest that WIMPs were created in the early universe in a manner similar to regular particles. These particles would make up what is called cold dark matter, which is believed to be responsible for the majority of dark matter. To explain the current abundance of dark matter, WIMP particles would need to be able to annihilate one another in a particular way, which happens to be consistent with the prediction that WIMPs have masses around 100 billion electron volts and interact through the electroweak force. This idea, often referred to as the WIMP miracle, is a remarkable match to predictions made by supersymmetric theories, which extend the standard model of particle physics. According to these theories, supersymmetry predicts the existence of stable partner particles that could potentially explain dark matter. Researchers have been actively searching for WIMPs by looking for the products of their annihilation, such as gamma rays, neutrinos, and cosmic rays emitted from nearby galaxies. Other experiments are designed to directly detect WIMPs by measuring their interactions with atomic nuclei, or even by attempting to create WIMPs in particle colliders like the Large Hadron Collider, LHC. However, by the early 2010s, experiments had failed to produce strong evidence for supersymmetry, and results from the LHC cast doubt on some of the simplest WIMP models. In the wake of this, scientists turned to other dark matter candidates, including axions. These hypothetical particles were first proposed in 1978 by physicists Frank Wilczek and Steven Weinberg as a solution to a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are extremely light and weakly interact with other particles, making them a promising candidate for dark matter. They could have been produced in the early universe and would still be present today, their abundance determined by their mass. Their extremely low mass also makes them a good candidate for solving some of the small-scale issues in the lambda cold dark matter, lambda CDM model, which is the leading cosmological model of the universe. As WIMP detection efforts faltered, axions have gained more attention, and recent developments suggest they might be able to explain some of the unresolved questions about dark matter. Another fascinating candidate for dark matter comes in the form of primordial black holes that could have formed in the incredibly dense regions of subatomic matter right after the Big Bang during a period of rapid cosmic expansion known as inflation. Unlike regular black holes, which form when massive stars collapse at the end of their lives, primordial black holes would have formed directly from dense matter. These black holes could have a wide range of masses, from incredibly tiny ones, even as small as atoms, to massive ones far beyond the size of typical stellar black holes. The idea of primordial black holes as dark matter candidates was first proposed in 1967 by Yakov Zeldovich and Igor Novikov, and later in 1971 by Stephen Hawking. The concept quickly gained traction as a potential explanation for dark matter. One of the advantages of primordial black holes is that the theoretical framework for black holes, based on general relativity, was already well established. The very existence of black holes, detected through their gravitational influence, lent support to this hypothesis. However, creating primordial black holes in the early universe would require very specific conditions, such as exotic forms of cosmic inflation or theories beyond the standard model of particle physics. In 2015, the detection of gravitational waves from the merger of black holes reignited interest in primordial black holes as dark matter. Some of these black holes appeared to have masses that seemed too large to have been formed by the collapse of stars, leading scientists to speculate that they could be primordial. Yet, studies looking for gravitational lensing effects from intermediate mass black holes, potential candidates for dark matter, found no evidence to support this hypothesis. Some researchers have suggested that the absence of evidence could be due to incorrect assumptions about the masses of these black holes, and further observations, including those from the James Webb Space Telescope, may provide more insight. Earlier, scientists believed that tiny primordial black holes might account for a significant portion of dark matter. However, in 2017, NASA's Voyager 1 spacecraft, which ventured beyond the influence of the Sun, measured the flow of positrons and electrons in deep space. The results were surprising. The detected particle flow was lower than expected, and the energy levels of the particles did not match predictions. This led researchers to conclude that tiny black holes, if they existed, were too rare to explain dark matter. Despite these challenges, the search for primordial black holes as dark matter candidates continues. New theories are emerging, exploring the potential for cooling dark matter in ways that could make it detectable. As of 2018, the mystery surrounding dark matter remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present. This only added more doubt to the existence of primordial black holes as a dark matter solution. But the investigation continues, and the future may yet hold new revelations that will help unlock the secrets of dark matter. Despite decades of intensive research, there remains a significant gap in our understanding of the universe's composition, particularly when it comes to dark matter. While astronomers have been able to detect and measure a range of masses and objects in space, there is still a mass range that is smaller than what current technology can detect using optical microlensing. This is a domain where primordial black holes might hold the key, potentially contributing entirely to the makeup of dark matter. However, this area of research remains a mystery, and scientists are continuing to explore new possibilities, challenging everything we thought we knew about the universe. If dark matter consists of particles that barely interact with normal matter, we are faced with a crucial question. Could these elusive particles form large, compact objects, such as planets, stars, or even black holes? Historically, the answer has been a definitive no, and there are several key reasons behind this. Regular matter can condense into dense objects like stars and planets because it can lose energy through various mechanisms. For instance, when particles fall inward due to gravity, they can lose energy, which enables them to slow down, cluster together, and form stable structures. Dark matter, on the other hand, seems to lack this ability. It doesn't interact strongly with other matter except through gravity, meaning it has few, if any, ways to shed energy. When dark matter particles are pulled inward by gravity, they simply speed up, heat up, and ultimately escape the gravitational pull, preventing the formation of any compact objects. This lack of energy loss means that dark matter particles remain diffuse and unable to condense in the same way regular matter does. Unlike normal matter, which interacts through multiple forces like gravity, electromagnetism, and the strong nuclear force, dark matter appears to interact almost exclusively through gravity and possibly weak interactions, though the latter is still speculative. This lack of diverse interactions means that dark matter doesn't have the same capability to form complex structures like atoms, stars, or galaxies. For example, in the cores of stars, particles undergo nuclear fusion, producing light and neutrinos as byproducts. In dark matter, however, no such interactions have been observed beyond gravity. Thus, dark matter remains elusive, failing to produce the detectable phenomena we observe in normal matter. Dark matter particles, if they exist, pass through every square centimeter of Earth millions, if not billions, of times per second. To explore these particles, many experiments have been designed to detect their presence. While WIMPs, weakly interacting massive particles, have long been the leading candidates for dark matter, other possibilities are being considered as well, such as axions, particles that could account for dark matter. These are being studied in experiments like the Axion Dark Matter Experiment, ADMX, which aims to detect them by observing the specific electromagnetic signatures they might leave behind. Another class of potential dark matter candidates includes heavy particles from a hidden sector, which would only interact with regular matter through gravity. There are two primary categories of experiments currently working to detect dark matter: direct detection and indirect detection. Direct detection experiments aim to observe the scattering of dark matter particles off atomic nuclei, trying to detect minute energy shifts in the process. These shifts are often on the order of just a few thousand electron volts. When dark matter interacts with an atom, it could release energy in the form of light or vibrations, which can be measured. To successfully detect such faint signals, these experiments must be conducted in environments that are as isolated as possible from external noise. Hence, many are carried out deep underground to shield them from cosmic radiation. Examples of these underground laboratories include the Stowe Mine, the Sudan Mine, and the Gran Sasso National Laboratory. Within these labs, two main technologies are commonly used: cryogenic detectors that measure heat generated by particle collisions in materials like germanium, and noble liquid detectors that detect light produced when dark matter particles interact with liquids like xenon or argon. Well-known experiments such as CDMS, CREST, Xenon, and LUX have been pioneers in these efforts. They specialize in distinguishing dark matter from background particles, which typically scatter off electrons, while dark matter particles tend to scatter off atomic nuclei. On the other hand, indirect detection experiments search for the effects of dark matter particles annihilating each other or breaking down into smaller particles. Although no direct detection of dark matter has yet been confirmed, these experiments have already helped to rule out certain properties for dark matter particles. One particularly intriguing claim comes from the Gamma Libra collaboration, which has detected a yearly variation in their data, potentially linked to Earth's motion through the dark matter cloud. However, other experiments like LUX and Super CDMS have not observed the same effect, creating a puzzle that remains unsolved. Some experiments aim to track the motion of dark matter particles, attempting to pinpoint the direction in which they are traveling based on the solar system's orbit around the galactic center. The idea is that the motion of the Earth through this dark matter cloud could create a detectable signature. Projects like the Dark Matter Directional Detector, DMTPC, and DRIFT are exploring this approach. In addition to these techniques, researchers are also investigating the potential for dark matter particles to interact with the Sun or the Earth, losing energy in the process. Such interactions could lead to the accumulation of dark matter in the centers of these celestial bodies, increasing the chances for particle collisions and destruction. This could result in the release of high-energy neutrinos, a potential sign of dark matter composed of WIMPs. Instruments like the Amanda, IceCube, and Antares neutrino observatories are actively searching for such signals. The detection of gravitational waves, first observed by LIGO in 2015, has opened up a new avenue for studying dark matter. This breakthrough has spurred experiments to detect dark matter in entirely new ways, especially if it exists as primordial black holes from the early universe. Some experiments have also searched for gamma rays that might be produced by the annihilation of dark matter particles. For instance, the Fermi Gamma Ray Space Telescope observed an unusually high number of gamma rays from the center of the Milky Way, possibly indicating dark matter destruction or some unknown astrophysical phenomenon. However, these observations are still debated, and further analysis is required to confirm their implications. Ground-based telescopes have also set limits on dark matter's possible influence on dwarf galaxies and galaxy groups, while the Pamela experiment detected an excess of positrons, which could be a sign of dark matter or some other exotic process. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays that could potentially be linked to dark matter interactions. Another promising method for detecting dark matter involves particle accelerators, such as the Large Hadron Collider, LHC. In these experiments, protons collide at extremely high speeds, potentially creating dark matter particles in the process. Although dark matter doesn't interact much with regular matter, it could be inferred from the energy and momentum missing from the collision, suggesting that dark matter particles were produced but not detected directly. As promising as these experiments are, any potential discovery of dark matter particles in such experiments must be confirmed by independent observations from both direct and indirect detection methods. Without this verification, the identification of new particles as dark matter remains speculative. Given that dark matter has yet to be identified definitively, alternative theories have emerged to explain some of the same cosmic phenomena. General relativity, which supports much of the evidence for dark matter, is well tested on the scale of the solar system. However, its applicability on galactic or cosmic scales remains uncertain. Some scientists argue that modifying general relativity could eliminate the need for dark matter altogether. Notable alternatives include modified Newtonian dynamics, MOND, a version of gravity that adjusts Newton's laws at low accelerations, and theories involving negative mass, dark fluid, or entropic gravity. However, these theories face significant challenges because the evidence for dark matter comes from many independent sources. While it might be possible to explain a single observation without invoking dark matter, explaining all the evidence without it is incredibly difficult. Some of these alternative theories have had limited success. For example, a 2016 test of gravitational lensing in entropic gravity and a 2020 measurement that supported MOND. Still, the majority of astrophysicists agree that while some modifications to general relativity may help explain certain observations, the overall data suggests that dark matter likely exists in some form. As we contemplate the origins of the universe, one of the most profound and enduring questions we face is, what existed before anything came into being? How did everything, matter, energy, space, emerge from what appears to be nothing? This question has haunted scientists, philosophers, and thinkers for centuries and remains at the core of many of our deepest inquiries into existence. At the heart of this mystery is the concept of nothingness, a void, an emptiness, a vacuum, existing long before the formation of atoms, stars, or galaxies. But this nothingness is far more complex and fascinating than we might initially imagine. It is not just an absence of matter. Rather, it is a peculiar state that possesses the potential to give birth to everything we know. To understand this concept of nothingness, we must first consider how we perceive it in our everyday lives. If we look at an empty room, we might say there is nothing in it. But even in this case, the room is filled with air, light, and the potential to hold something else. In contrast, the nothing that cosmologists refer to is far more profound, an absolute void devoid not only of matter, but also of energy and even space itself. It is the true nothingness that existed before the universe. Imagine a time before the Big Bang. No stars, no planets, no atoms, and no space as we understand it. In fact, the very concept of space didn't exist in the way we know it today. This was a time when the laws of physics, as we currently understand them, did not operate in the same way. Everything we now consider as something was still in a state of potential, yet to be created. So what was this nothingness like? Was it truly empty, or was something more subtle and strange occurring within the void? According to modern physics, this emptiness wasn't as inert as it might seem. In fact, this vacuum of nothingness may have been the birthplace of everything we now observe, the matter, energy, and forces that make up our universe. The age-old question of how something can arise from nothing has captivated both philosophers and scientists alike. It seems like a paradox, a dilemma so paradoxical that it stretches our basic understanding of logic and reason. If there was nothing, how could anything possibly come into existence? How could an entire universe emerge from an absolute void? At first glance, this idea defies all common sense. After all, How can a universe full of stars, galaxies, and the very matter that makes up everything we see simply come into being from nothing? But here's where modern science, particularly the realm of quantum mechanics, presents a surprising and rather astonishing answer. In the world of quantum physics, the concept of nothing is not as empty or devoid as it might seem. In fact, the very fabric of empty space, the so-called vacuum, is teeming with strange, unpredictable activity. This seemingly empty vacuum is not truly empty. Instead, it is the stage for what scientists call quantum fluctuations, a phenomenon that challenges our most fundamental ideas about what empty space actually means. These quantum fluctuations are brief, spontaneous changes in the energy levels of what we perceive as empty space. These fluctuations can occur without any apparent cause, creating tiny bursts of energy that appear and disappear in an incredibly short span of time. Although these fluctuations are fleeting and their effects are incredibly small, they are real. They can be measured, observed, and studied through the principles of quantum mechanics. What is truly mind-blowing is that even in a perfect vacuum where no particles exist, this energy still fluctuates, suggesting that even the void, the nothingness, is not truly void at all. This is a concept that goes far beyond what we can observe with the naked eye. Yet, through the sophisticated tools of quantum physics, we can peer into the depths of this invisible realm and see how this activity can shape the universe itself. When we look at the origins of the universe, these quantum fluctuations take on even more significance. The Big Bang, an event that took place around 8 billion years ago, was not a traditional explosion in space. It wasn't an event that happened in space. It was rather an event that created space itself. At the beginning, all the energy and matter that would eventually form everything in the universe were packed into a singularity, a point of infinite density and heat. But how did this singularity come to be? And how did something arise from what appeared to be nothing? The answer, according to some scientists, lies in the very quantum fluctuations we've just discussed. It's suggested that these fluctuations in the quantum vacuum could have set the stage for the Big Bang. Essentially, the vacuum, in a sense, decided to shake things up by creating particles, energy, and ultimately the universe itself. This process, known as quantum creation, proposes that the empty vacuum of space is not empty at all. In fact, space itself is capable of fluctuation, and under the right conditions, these fluctuations can give rise to matter and energy. This hypothesis is revolutionary because it suggests that the very laws of physics, which govern the behavior of particles and energy in our universe, might have emerged from this very nothingness that existed before the birth of everything we know. In this view, the universe wasn't created in a single dramatic event, but rather through a continuous process of quantum fluctuations that unfolded in the fabric of space-time. If the universe can emerge from nothing in this manner, then what about the laws of physics? How can we explain the consistency of these laws if they too were born from a void, from a place where no laws existed? This question, perhaps the most profound one in science, pushes our understanding of reality to its limits. But it is precisely here, in the face of such mysteries, that the elegance of science shines through. One important concept to grasp is that the laws of physics are not arbitrary. They arise from the intrinsic properties of the universe. When we speak of these laws, we refer to the fundamental principles that govern the behavior of matter, energy, and space itself. These laws are what allow gravity to pull, particles to interact, and energy to manifest in a way that is predictable and consistent. These include the fundamental forces such as gravity, electromagnetism, and the strong and weak nuclear forces, along with the principles of thermodynamics that govern the flow of energy and the direction of entropy. But where did these laws come from? How did they emerge from the very nothingness that existed before the universe? According to modern theories, the laws of physics weren't fixed at the time of the Big Bang. In fact, in the earliest moments of the universe, the laws might have been vastly different from how we understand them today. This period, which occurred just moments after the Big Bang, is thought to have seen the universe expand at an incredible rate. This rapid expansion is known as inflation. During this inflationary period, space itself stretched at a mind-boggling pace, and the fundamental forces that govern our universe, gravity, electromagnetism, and the nuclear forces might not have been distinct from one another. Instead, they could have been unified into a single force, known as a superforce. As the universe cooled, these forces separated, evolving into the distinct forces that we recognize today. This idea that the laws of physics could change as the universe evolved is difficult to grasp, yet it is backed by both theoretical predictions and observational data. As the universe cooled and expanded, the conditions changed, and the forces governing matter and energy began to assume their present-day forms. It's as though the universe started with a set of very simple, general principles that over time grew into the highly structured and intricate web of laws that govern everything we know. The universe, from this perspective, could have evolved from a quantum fluctuation, a tiny spark of energy in the vast emptiness, into the highly organized, law-abiding cosmos that we now observe. This gives us a new way of looking at the laws of physics. They are not external constructs imposed upon the universe, but rather they are woven into the very fabric of space-time itself. They emerged naturally from the conditions that arose after the Big Bang, as the universe cooled, expanded, and evolved. The quantum vacuum, or empty space, is far from empty. It is brimming with potential. At its most fundamental level, space is filled with quantum fields that permeate the entire universe. These fields are the building blocks of mass, energy, and the very structure of space-time. Even in the absence of any visible matter or energy, these quantum fields are still active. They fluctuate, interact, and give rise to the strange phenomena of quantum mechanics, such as particle-antiparticle pairs that spontaneously appear and vanish in an instant. This activity is what gives rise to the unpredictable yet measurable events that define the quantum world. Classical physics taught us to think of empty space as a vacuum, a void with no matter or energy. But in the quantum world, nothing is further from the truth. Empty space is, in fact, a dynamic, ever-changing field of energy, full of possibilities. It is a fertile ground from which anything can arise. In this sense, the quantum vacuum can be seen as the ultimate source of creation, where every particle, every force, and every fundamental interaction is born. The creation of the universe is a story that begins not with atoms or molecules, but with the smallest of particles, the quarks. These minuscule particles are the building blocks of protons and neutrons, the components that make up the atomic nucleus. Quarks are so tiny that they cannot be observed directly. To study them, scientists use powerful particle accelerators, smashing atoms together at nearly the speed of light, revealing the deeper components of matter. Quarks come in 6 different types, or flavors: up, charm, strange, top, and bottom. While the up and down quarks are the most common, making up the protons and neutrons found in ordinary matter, the other 4, charm, strange, top, and bottom, are rarer and only exist in the extreme environments of particle collisions or the early universe. These quarks are held together by a powerful force known as the strong nuclear force, one of the 4 fundamental forces of nature. This force is so strong that it binds quarks together into protons and neutrons, preventing them from flying apart. Unlike electrons, which belong to a separate group of particles called leptons, quarks never exist alone. They always form larger particles, such as protons and neutrons that make up the atomic nucleus. Electrons, in turn, orbit around these nuclei, giving atoms their structure and allowing them to interact with one another. The story of quarks begins at the very dawn of the universe. In the earliest moments of the Big Bang, around 13.8 billion years ago, the universe was a searing cauldron of energy. During the first fraction of a second, the energy began to cool enough to allow quarks to form. For a brief moment, quarks existed freely in this intense energy field, but as the universe continued to expand and cool, the strong nuclear force pulled them together, creating the first protons and neutrons. These building blocks would go on to form the first atomic nuclei, setting the stage for the formation of atoms, stars, galaxies, and eventually the universe as we know it. In the most fundamental sense, the universe, everything that exists, from the smallest quark to the largest galaxy, emerged from nothing. And in a way, that nothing was never truly nothing. It was teeming with potential, ready to give birth to everything we observe today. The birth and evolution of the universe as we know it has been a journey through extreme heat, chaos, and transformation. While the exact conditions of the early universe remain a topic of intense study, we do know that it was an unimaginable furnace of energy and particles. In those first moments after the Big Bang, the universe was far too hot for atoms to form. It took nearly 38,000 years for the temperature to drop enough for electrons to finally join the nuclei, creating the first stable atoms, primarily hydrogen and helium. Over the next billions of years, these simple atoms began to interact, clumping together under gravity to form stars, planets, and eventually the galaxies and complex structures that make up our universe today. But even this process, which seems so fundamental to the world we experience, was preceded by a discovery that would challenge our deepest understanding of the building blocks of matter itself. For centuries, scientists believed that protons and neutrons, those small, dense particles at the heart of atoms, were the smallest and most fundamental units of matter. However, in the 1960s, two physicists, Murray Gell-Mann and George Zweig, proposed a radical idea. They suggested that protons and neutrons, instead of being indivisible, were made up of even smaller particles, which they named quarks. This theory was initially met with skepticism, but in the years that followed, high-energy particle experiments confirmed their predictions. Through the use of particle accelerators, scientists were able to smash protons and neutrons together at incredible speeds, unveiling the inner structure of these particles and revealing the quarks hidden within. As these discoveries evolved, so did our understanding of the universe's fundamental forces. Quarks are not merely small pieces inside atoms, they are the very foundation of matter itself. Their interactions govern much of the processes that power the universe. For instance, quarks are essential to nuclear energy, the force that fuels stars and enables nuclear reactors to produce electricity. But their significance extends beyond energy production. Quarks have also led to breakthroughs in medicine, technology, and space exploration. Unlike electrons, which can exist as free particles moving independently, quarks never exist alone. This behavior is due to a property known as confinement. Even though quarks are smaller than the smallest atoms, they are bound together by a force so strong that they can only exist in groups, never independently. These color charges, as physicists call them, are not colors in the way we normally think of them. Instead, they describe the way quarks interact, using terms like red, green, and blue. This naming convention helps explain how quarks come together and form composite particles, which in turn make up the nuclei of atoms. One of the most fascinating aspects of quarks is their mass. The top quark, for example, is incredibly heavy, about as massive as a gold atom, despite being much smaller than a proton. This fact highlights the strange and exotic nature of quarks, which exist in a variety of other particles beyond protons and neutrons. In addition to these familiar particles, scientists have also discovered exotic particles like pions, kaons, and tetraquarks, which exhibit bizarre and unpredictable behaviors that challenge our understanding of particle physics. The glue that holds quarks together is called the gluon, a particle that carries the strong nuclear force. This force is one of the four fundamental forces of nature and is responsible for binding quarks together to form larger particles like protons and neutrons. Without gluons, quarks would never form the stable particles that make up atoms, and without these stable atoms, the universe as we know it would not exist. Gluons essentially act as the glue that holds the universe together on a subatomic scale, and their importance cannot be overstated. In the early universe, immediately following the Big Bang, conditions were extreme. Scientists estimate that within the first fraction of a second, less than a trillionth of a second, after the birth of the universe, the cosmos was a seething soup of quarks and gluons, an environment known as quark-gluon plasma. In this state of matter, quarks and gluons were free to move independently, unbound by the forces that would later form protons, neutrons, and other particles. The temperature at this time was staggeringly high, more than 1 trillion degrees Celsius, far hotter than the core of any star. In such a blistering hot environment, quarks and gluons did not yet form stable particles. Instead, they were in a constant state of violent interaction, colliding and recombining in a turbulent dance of energy and matter. As the universe expanded and cooled, however, the temperature dropped to a point where quarks and gluons began to stick together. This process, known as hadronization, marked a critical point in the universe's evolution. During hadronization, quarks combined in specific ways to form hadrons, composite particles like protons and neutrons, which would serve as the building blocks of atomic nuclei. The formation of protons and neutrons was a turning point. Without this process, the universe would never have produced the stable matter needed to form the stars, galaxies, and eventually the elements that make up the world we live in today. The interactions between quarks and gluons during this era shaped everything, from the smallest atomic particles to the largest cosmic structures. At the heart of this process was the strong nuclear force, the most powerful of nature's fundamental forces. Unlike gravity, which acts over vast distances, or electromagnetism, which affects charged particles, the strong force operates only at extremely short ranges, inside atomic nuclei. This force is carried by gluons, and it is so powerful that it overcomes the repulsion between positively charged protons inside atomic nuclei. Without this force, quarks could not form stable particles, and atomic nuclei would never have formed, preventing the universe from taking the shape we observe today. Once quarks had combined into protons and neutrons, these particles could begin to fuse together to form the first atomic nuclei. This process, nuclear fusion, played a crucial role in the formation of the elements that populate the universe. However, the universe was still too hot for electrons to settle into stable orbits around atomic nuclei, meaning atoms had yet to form. It wasn't until around 380,000 years after the Big Bang, as the universe cooled further, that electrons were able to combine with nuclei, creating the first neutral atoms. This process, known as recombination, marked the beginning of the universe as we know it today. For the first time, light could travel freely, and the universe became transparent. This event led to the formation of the cosmic microwave background radiation, a faint glow still detectable by scientists today. It serves as a snapshot of the universe at that moment in time, offering a glimpse into the very early stages of the cosmos. Understanding how quarks and gluons behaved in the early universe is more than a theoretical pursuit. It is a key to understanding the fundamental nature of matter itself. To recreate the conditions of quark-gluon plasma, scientists have turned to high-energy particle colliders, such as the Large Hadron Collider, LHC, in Switzerland, and the Relativistic Heavy Ion Collider, RHIC, in the United States. By smashing heavy atomic nuclei, such as gold or lead, at nearly the speed of light, scientists can generate the extreme temperatures and pressures that existed in the early universe. These experiments allow physicists to study how quarks and gluons interact, offering insights into the forces that shaped the birth of the universe. Through these studies, scientists have made one of the most remarkable discoveries in recent years. Quark-gluon plasma behaves like an almost perfect fluid, flowing with near-zero resistance. This revelation has had profound implications for our understanding of the fundamental forces that shape the universe. The interactions of quarks and gluons and the way they shaped the early universe continue to be a focal point of scientific research, helping us uncover the deepest mysteries of our cosmos. The intricate dance of quarks and gluons in the first moments of the universe played a foundational role in shaping everything we observe today. The strong nuclear force, gluons, and quarks themselves form the bedrock upon which the universe was built. As scientists continue to explore the mysteries of these fundamental particles, we move ever closer to understanding the true nature of reality. The universe as we know it would not exist in its present form if the tiniest particles had not come together in such a precise, unimaginable way. The very fabric of existence hinges on the interactions of fundamental particles that, when combined, give rise to everything around us. Without these particles, there would be no protons, neutrons, or atoms. In fact, the concept of stars, planets, and life itself would be entirely inconceivable. One of the keys to understanding this intricate reality lies in the study of quarks and gluons, two of the most fundamental particles that make up all matter. By delving into their behavior, scientists are unlocking the secrets of how the universe operates at its most basic level. Quarks and gluons, which once roamed freely in the violent and chaotic conditions of the early universe, are now bound together within stable structures that form the very core of the cosmos. Quark confinement, a fascinating and complex phenomenon, explains why these particles never exist alone. Unlike electrons, which can roam freely, quarks are always found in groups. These particles combine in sets of three to create protons and neutrons, the building blocks of atomic nuclei, or pair up in twos to form mesons, particles that mediate strong forces. This grouping happens due to a force so powerful that attempting to separate quarks results in an even greater pull that forces them back together. This force, known as the strong nuclear force, is by far the most intense fundamental force in nature, far stronger than gravity or even electromagnetism. To visualize this, imagine two quarks tethered together by a rubber band. When you try to pull them apart, the band stretches, storing more energy. However, instead of snapping, the energy doesn't dissipate. Instead, it transforms into new quarks and antiquarks, which then immediately form new particles. This explains why quarks are never isolated. They are always confined within larger particles, bound together by an invisible yet incredibly powerful force. This force can be traced back to the earliest moments after the Big Bang, a time when the universe was unimaginably hot and dense. During this period, quarks and gluons roamed freely in a high-energy state, resembling steam molecules in a pot of boiling water. But as the universe expanded and cooled, these quarks began to combine, bound by the strong nuclear force. Initially, they formed triplets of quarks, which eventually became protons and neutrons, particles that would go on to form the atomic nuclei at the heart of every atom. The specific combination of quarks that make up protons and neutrons is crucial to the structure of matter. A proton consists of two up quarks and one down quark, while a neutron contains two down quarks and one up quark. The immense force that holds these quarks together is so strong that no natural process could ever break them apart. This marks the birth of atomic nuclei, the very foundation of all matter. Without quark confinement, protons and neutrons could not exist. Without them, atoms could never have formed, and without atoms, there would be no elements, no molecules, and no life as we know it. The strong nuclear force that binds quarks inside protons and neutrons also plays a crucial role at a larger scale. It holds the protons and neutrons together within atomic nuclei. Without it, atomic nuclei would disintegrate due to the repulsion between positively charged protons. The gluons, the force carriers of the strong nuclear force, act like an invisible rope, pulling the protons and neutrons tightly together, preventing them from flying apart. For decades, scientists have worked tirelessly to understand the full extent of quark confinement. The theory that governs this phenomenon is known as quantum chromodynamics, QCD. According to QCD, quarks possess a property called color charge, similar to the electric charge of electrons, but with three distinct types: red, green, and blue. The strong nuclear force ensures that quarks combine in a way that their colors cancel out, ensuring that they remain confined within larger particles. This perpetual confinement is one of the most remarkable rules of nature, and it is vital for the existence of stable matter. The concept of time is also central to understanding the creation of the universe. Time, an invisible force that dictates the sequence of events, is essential for any process of change or development. Without time, the universe would be in a state of eternal stillness, no motion, no transformation, no progression. The idea of change itself would be meaningless. Imagine throwing a ball. Without time, the ball would not move. It would remain frozen in place, unable to travel through the air or fall to the ground. Similarly, the process of cooking food, from raw to cooked, would be impossible without time, as change and transformation could not occur. Without time, none of the processes we take for granted could unfold. The birth of the universe itself, from the chaotic explosion of the Big Bang to the formation of the first atoms, required the passage of time. In the first few moments after the Big Bang, there was no structure, no galaxies, no stars, no planets, just an ocean of pure energy. But as the universe expanded and cooled over time, this energy began to condense into subatomic particles, which eventually formed atoms. These first atoms were predominantly hydrogen and helium, the simplest and lightest elements in existence. This entire transformation was a process that unfolded over time. If time did not exist, the universe would have remained frozen, incapable of evolving or progressing. Without time, atoms could not form. Without atoms, there could be no molecules, no elements, and certainly no life. The same rule applies to the formation of any complex structure. For an atom to come together, particles must interact, combine, and change, actions that can only occur if time is passing. Some philosophers and scientists have questioned whether time is a real, intrinsic property of the universe or merely a construct of the human mind. Could the universe exist outside of time? Could time itself be an illusion, something invented by humans to make sense of their world? Certain theories in cosmology suggest that, in the earliest moments of the universe, time may not have existed in the way we understand it today. Some researchers propose that time, space, and matter all emerged simultaneously in the aftermath of the Big Bang. If this is true, then before the Big Bang, time as we know it did not exist, and the universe may have been in a state where change and progression were impossible. This raises profound questions. How did the universe transition from a state of nothingness to something? Without time, how could anything move, change, or come into existence? If time did not exist, the universe would remain frozen in an eternal, unchanging moment. Nothing could evolve. No matter could come together to form the structures we see today, from galaxies to the tiniest atoms. Space itself is inextricably linked to the concept of time and the formation of matter. As the universe expanded, space itself stretched and created room for particles to move, interact, and combine. This process was essential for the formation of atoms. In fact, space provides the stage upon which all of these processes occur. If space did not exist, or if it were compressed into an infinitely small point, as it may have been in the moments before the Big Bang, there would have been no room for particles to interact, and thus no atoms could have formed. This idea touches on the concept of a singularity, a point of infinite density where the laws of physics break down. It is believed that before the Big Bang, the entire universe existed in a singularity, a state where time and space were not as we understand them today. In such a state, atoms, if they even existed in any recognizable form, could not have come into being. The expansion of space created the conditions necessary for atoms to form, leading to the creation of the universe as we know it. Space itself is not an empty vacuum, but an active part of the universe. Albert Einstein's theory of general relativity revealed that space and time are intricately woven together into a fabric known as space-time. This fabric is not passive. It is influenced by the presence of matter. Massive objects like stars and planets warp the fabric of space-time around them, creating what we experience as gravity. In this way, atoms do not just need space to form, they also influence the very structure of space itself. This dynamic relationship between matter and space is one of the reasons why the universe continues to expand. As galaxies move apart, new space is created between them, allowing more atoms to interact, combine, and form new structures. One of the more mysterious aspects of the universe is antimatter. This strange material is essentially the mirror image of ordinary matter, made up of particles called antiparticles. These antiparticles possess opposite properties to those of regular particles, including reversed electric charge and a reversed behavior in response to forces like gravity. While antimatter might sound like something from science fiction, it is very real and exists in nature. It is produced in powerful cosmic events, such as high-energy collisions between cosmic rays, and can also result from certain types of radioactive decay. However, antimatter is incredibly rare, and when it comes into contact with normal matter, it annihilates instantly, releasing vast amounts of energy. In the lab, scientists have managed to produce tiny amounts of antimatter in particle accelerators, where they smash particles together at high speeds. Yet, even with all our technological advancements, only minuscule amounts, measured in billionths of a gram, have been produced. One of the major challenges is storing and studying antimatter. It must be kept in magnetic and electric traps, as it cannot come into contact with regular matter. Despite its rarity, antimatter plays an important role in science and medicine. For instance, in positron emission tomography, PET scans, a form of medical imaging, antimatter helps doctors diagnose diseases, including cancer. It is also used in certain types of radiation therapy to treat tumors, highlighting just how far-reaching the influence of these elusive particles is, even in our everyday lives. Antimatter, once a concept confined to the realm of science fiction, has slowly found its place within the realms of serious scientific inquiry. Its potential is vast and its mysteries profound. Today, antimatter is no longer just a theoretical idea, but a powerful tool in scientific and industrial applications. One of its most notable uses is in specialized imaging techniques, where its properties can be harnessed for groundbreaking technologies such as positron emission tomography, (PTET) scans. These imaging systems rely on the fact that when an antiparticle meets its matching normal particle, a dramatic and energetic event unfolds: annihilation. During this annihilation process, both the matter and antimatter particles are completely destroyed in a violent release of energy, most often in the form of gamma rays, high-energy light. This burst of energy can sometimes include additional subatomic particles. The amount of energy released during this reaction is directly proportional to the mass of the particles involved, following Albert Einstein's famous equation E=mc². This equation reveals the profound truth that mass can be converted into energy with astonishing efficiency. In theory, if humans could somehow amass and control large quantities of antimatter, it would become one of the most efficient energy sources known to humanity. A small amount of antimatter could, in theory, provide enough energy to power entire cities or fuel spacecraft traveling across vast stretches of interstellar space. However, despite its immense potential, the cost and difficulty of producing and containing antimatter make such applications far beyond our current capabilities. For now, the possibility of antimatter as an energy source remains a distant dream. An even more puzzling and intriguing mystery lies at the heart of the universe's origins. According to the prevailing theories of cosmology, when the universe was formed in the Big Bang, there should have been equal amounts of matter and antimatter. However, the observable universe appears to be made almost entirely of normal matter, with very little antimatter to be found. This striking imbalance between matter and antimatter, known as baryogenesis, represents one of the greatest unsolved enigmas in physics. Why, if matter and antimatter were created in equal quantities, didn't they annihilate each other completely? What mechanism allowed matter to prevail and antimatter to be so scarce? These are questions that scientists are still actively exploring, seeking an explanation for the asymmetric nature of the cosmos. Just as protons and electrons combine to form atoms in the world of normal matter, their counterparts in antimatter, the antiprotons and positrons, can similarly combine to form antiatoms. The simplest of these antiatoms is antihydrogen, consisting of a positron orbiting an antiproton, mirroring the structure of a hydrogen atom in regular matter. In laboratory settings, scientists have successfully created antihydrogen atoms and in more recent times have even synthesized slightly more complex antihelium nuclei. These breakthroughs offer tantalizing hints that entire antimatter elements could, in theory, exist. Before the modern understanding of antimatter was fully realized, certain scientists speculated on the existence of negative matter, a strange form of matter that would possess negative mass and possibly even reverse gravity. In the 1880s, a researcher by the name of William Hicks entertained the idea of negative gravity within a theory involving swirling cosmic vortices. Later, in the 1890s, Carl Pearson introduced the idea of squirts and sinks in ether theory, positing that normal matter flowed out of certain regions of space while negative matter was drawn in elsewhere. However, these early concepts were abandoned as modern physics developed more accurate models of energy, forces, and matter. The term antimatter itself was first coined by the scientist Arthur Schuster in 1898. Schuster introduced the term in a pair of whimsical letters he sent to the scientific journal Nature. In these letters, he speculated about the existence of anti-atoms, atoms that would behave as the exact opposite of regular atoms. Schuster even imagined entire solar systems composed of antimatter, proposing that if matter and antimatter came into contact, they would completely annihilate each other. Interestingly, Schuster also believed that antimatter would possess negative gravity, causing it to fall upward rather than downward. While Schuster's musings were based on imagination rather than solid evidence, they helped spark the scientific curiosity that would eventually lead to our modern understanding of antimatter. The real breakthrough in the study of antimatter came in 1928 when the physicist Paul Dirac published a revolutionary paper that described the behavior of electrons, the negatively charged particles that reside in atoms. His mathematical equations suggested the existence of a mirror image version of the electron, what we now know as the positron, an antimatter counterpart to the electron. Although Dirac's work pointed in this direction, he didn't immediately recognize the full implications of his findings. It was the renowned physicist J. Robert Oppenheimer who, in 1930, took Dirac's equations and correctly interpreted them. In his own paper, Oppenheimer theorized the existence of a positively charged electron, which could not be a proton, as protons are much heavier. Dirac expanded on this idea in 1931, officially describing positrons as anti-electrons. In 1932, just a year after Dirac's theoretical prediction, the physicist Carl D. Anderson made an astonishing discovery. While studying cosmic rays, high-energy particles coming from outer space, he detected particles that behaved exactly like positrons. Anderson was the first to observe these antimatter particles, and he gave them the name positron, a term which simply means positive electron. Interestingly, although Dirac never used the term antimatter in his work, the term naturally emerged as a way to describe all particles that corresponded to normal matter particles, but with opposite properties: anti-electrons, antiprotons, and so on. Around the same time, in 1929, a scientist named Charles Janet proposed an intriguing idea about what an entire periodic table of antimatter elements might look like. One of the most intriguing theoretical ideas related to antimatter is the Feynman-Stuckelberg interpretation, a concept developed by physicist Richard Feynman. According to this theory, antimatter behaves just like normal matter, except that it moves backward in time. This counterintuitive idea has been widely embraced in the world of modern physics and is a key concept in Feynman diagrams, which are used to visualize how tiny particles interact. These diagrams help scientists predict the behavior of matter and antimatter in high-energy environments. To differentiate between matter and antimatter, physicists use specific notations. For instance, a proton is represented by the symbol P, while its antimatter counterpart, the antiproton, is written as P. This same logic applies to quarks, the building blocks of protons and neutrons. A proton consists of 3 quarks, 2 up quarks, and 1 down quark, while an antiproton is made up of 3 antiquarks, 2 anti-up quarks, and 1 anti-down quark. Similarly, an electron, which has a negative charge, is written as E, and its antimatter counterpart, the positron, is written as E+, since it carries a positive charge. One of the most fascinating questions surrounding antimatter is whether it behaves differently than normal matter when exposed to gravity. For a time, it was hypothesized that antimatter might fall upward, contrary to the behavior of regular matter. However, recent experiments have dispelled this idea. In a remarkable study, scientists created a thin, extremely cold gas of antihydrogen atoms and trapped them in a magnetic bottle to prevent them from coming into contact with normal matter. As the magnetic fields were gradually weakened, allowing the anti-atoms to escape, the scientists discovered that most of the antihydrogen atoms fell downward, just as regular matter does. This confirmed that antimatter responds to gravity in the same way as matter does, contradicting earlier speculations. There are strong theoretical reasons to believe that, apart from having opposite electric charges, matter and antimatter are virtually identical in all other respects. In fact, if we were to create an entire universe composed of antimatter, it would look and behave exactly like our own, except with all the charges flipped. This symmetry suggests that an antiparticle must share the same mass, lifespan, and other physical characteristics as its corresponding particle of matter. The implications of this symmetry are profound. It even raises the possibility that antimatter stars, sometimes referred to as anti-stars, could exist somewhere in the universe. If such a star were discovered, it would shine just like a regular star made entirely of antimatter. To test this theory, in 2006, scientists working with the ALPHA experiment studied the behavior of anti-hydrogen atoms and observed how they transitioned between their 2 lowest energy states. Remarkably, their results mirrored those of normal hydrogen atoms, proving that quantum mechanics applies to antimatter in the same way it does to regular matter. Despite all the progress made in understanding antimatter, there is still much to learn. Our universe appears to be predominantly composed of normal matter, and scientists have yet to detect any large regions of space dominated by antimatter. If such regions existed, we would expect to see powerful gamma-ray emissions at the boundaries where matter and antimatter collide and annihilate. However, no such signals have been detected, further reinforcing the idea that antimatter is scarce in our universe. Antimatter does occasionally form, albeit in tiny quantities, in areas where energetic particle collisions take place. For example, when cosmic rays, high-speed particles traveling through space, collide with Earth's atmosphere, they can produce small amounts of antimatter in the form of antiparticles. However, these antiparticles are fleeting and quickly annihilate with normal matter, releasing bursts of energy in the process. In space, particularly in the vicinity of supermassive black holes and neutron stars, antimatter is also created during powerful cosmic events. In 2003, the European Space Agency's integral satellite observed a massive cloud of antimatter floating near the center of our galaxy, the Milky Way. This cloud, unevenly distributed, appears to align with the positions of certain X-ray emitting star systems, suggesting that intense cosmic activity is responsible for generating antimatter in these regions. As matter falls into these extreme objects, it gains vast amounts of energy, leading to the production of antimatter in the form of electron-positron pairs. The continued study of antimatter promises to unlock many more secrets of the universe, offering insights into the very fabric of existence. Antimatter, a substance both elusive and fascinating, remains one of the most enigmatic aspects of modern physics. While its properties are known, the precise mechanisms behind its creation and behavior are still shrouded in mystery. The existence of antimatter challenges our very understanding of the universe, especially when we consider that it is almost completely absent in the cosmos today, even though it seems to have been created in equal quantities with ordinary matter during the early moments of the universe. Scientists have been pursuing this mystery for decades, piecing together a picture of antimatter's role in both the cosmos and on Earth, but there is still much that we do not understand. Some researchers have even proposed the existence of entire galaxies composed primarily of antimatter. These galaxies, if they exist, would mirror the structure of regular matter galaxies. Antimatter, after all, obeys the same physical and chemical laws as matter, meaning the stars, planets, and other celestial bodies within them would emit and absorb light in the same way. This makes antimatter galaxies nearly indistinguishable from the regular ones that populate the observable universe. NASA has been spearheading efforts to detect antimatter in deep space, primarily by searching for gamma rays. When antimatter collides with matter, it annihilates, releasing intense bursts of radiation, particularly in the form of gamma rays. These telltale signals would provide scientists with the evidence they need to confirm the existence of antimatter galaxies. However, despite extensive searches, no such signals have been detected yet, suggesting that the universe is overwhelmingly made up of ordinary matter. In 2017, a groundbreaking achievement occurred in the study of antimatter at CERN, the European Organization for Nuclear Research. Working on an experiment known as BASE, scientists achieved an unprecedented level of precision in measuring the magnetic properties of an antiproton, the antimatter counterpart to the proton. They discovered that the magnetic moment of the antiproton was almost identical to that of the proton, with a discrepancy of just 1.5 parts per billion. This discovery lent strong support to the idea of CPT symmetry, a fundamental principle in physics that suggests the laws of the universe should apply equally to both matter and antimatter. It was a significant moment in the history of antimatter research, as it marked the first time a property of antimatter had been measured more accurately than its matter counterpart. Another monumental step forward came in 2018 when scientists in Italy successfully demonstrated antimatter quantum interference for the first time. Conducted at the positron laboratory in the town of Co, this experiment, led by physicist Marco Gambacci, provided new insights into how antimatter behaves at the quantum level. The findings were groundbreaking, offering potential pathways to deepen our understanding of quantum mechanics and the fundamental nature of the universe. Yet antimatter isn't confined to distant galaxies or high-energy physics labs. it is also produced naturally on Earth in several ways. For example, certain radioactive elements, such as potassium-40, release positrons, particles of antimatter, during their natural decay processes. Additionally, when high-energy gamma rays interact with matter, they can generate positrons as well. A more exotic form of antimatter, the antineutrino, is produced through a different type of radioactive decay known as beta decay. Cosmic rays, which constantly bombard Earth's atmosphere, also contain a variety of antiparticles, including positrons and antiprotons. In 2011, a surprising discovery further expanded our understanding of antimatter's natural origins. Researchers from the American Astronomical Society found that thunderstorms could produce positrons. The mechanism behind this is as dramatic as the phenomenon itself. Intense electric fields within storm clouds accelerate electrons to nearly the speed of light, producing bursts of gamma rays. These gamma rays, upon colliding with the atmosphere, create antimatter. This discovery underscored the notion that even common weather phenomena can lead to the formation of antimatter under the right conditions. Antimatter is also present closer to home in the Van Allen radiation belts, the two vast regions of charged particles trapped by Earth's magnetic field. Using the Pamela spacecraft, scientists detected antiprotons within these radiation belts. This discovery suggested that antimatter could exist in stable forms near Earth, a phenomenon that was once thought to be impossible. Furthermore, antimatter can also be created in places with extremely high temperatures, such as near supermassive black holes or neutron stars. These high-energy environments provide the necessary conditions for matter and antimatter to emerge in particle pairs. In the earliest moments of the universe, during a period known as baryogenesis, matter and antimatter were created in almost equal amounts. However, something happened that caused this delicate balance to shift, leading to the universe as we know it today, dominated by regular matter. This imbalance, known as baryon asymmetry, is one of the biggest unsolved mysteries in physics. Scientists have speculated that this anomaly could be linked to a phenomenon known as CP symmetry violation, which has been observed in certain subatomic interactions. The mystery deepens as astronomers continue to observe extreme cosmic events that produce antimatter in copious amounts. The formation of black holes and neutron stars, for example, generates enormous amounts of positron-electron plasma. These exotic particles are ejected into space in high-energy jets that can stretch for vast distances. These cosmic phenomena have been shown to produce bursts of antimatter, adding more complexity to the puzzle of antimatter's role in the universe. One particularly puzzling discovery came from the European Space Agency's Integral satellite, which detected a massive cloud of antimatter near the center of our galaxy. This cloud, however, is not uniformly spread out. Instead, it coincides with areas where certain X-ray emitting star systems exist, systems that are known to harbor neutron stars and black holes. The current theory suggests that as regular matter falls into these supermassive objects, it gains tremendous amounts of energy, leading to the formation of antimatter in the form of electron-positron pairs. However, the exact mechanics behind this process remain unclear, leaving researchers with more questions than answers. The study of antimatter is far from over, and as new discoveries continue to unfold, the quest to unlock the secrets of this elusive substance drives scientists to push the boundaries of our understanding. The possibility that antimatter may be present in large quantities, especially in the most extreme regions of space, continues to captivate the imagination of researchers. Whether antimatter galaxies exist, or whether the universe is truly dominated by ordinary matter, one thing is certain: antimatter is a key piece of the cosmic puzzle, and its study promises to reshape our understanding of the fundamental laws that govern the universe. As we peer deeper into the vastness of space and study the behavior of antimatter in laboratories on Earth, the questions that remain: why antimatter is so rare, how it behaves in extreme environments, and how it could shape the future of physics, are still unanswered. Yet, the search for answers continues, driving humanity closer to understanding one of the most profound mysteries of the universe. However, today, the universe is predominantly filled with matter, and antimatter, its elusive counterpart, is almost non-existent. This strange imbalance, known as baryon asymmetry, stands as one of the most perplexing riddles in modern physics. Scientists are convinced that understanding the cause of this asymmetry might hold the key to unraveling some of the deepest mysteries of the cosmos. A prominent theory suggests that this imbalance could be connected to a phenomenon known as CP symmetry violation. This refers to the breaking of the combined symmetry of charge conjugation, C, and parity P, which has been observed in certain interactions between subatomic particles. If researchers can pinpoint the exact reason for the dominance of matter over antimatter, it could offer profound insights into why the universe, as we know it, exists at all. Recent space observations have revealed that some of the most extreme and dynamic events in the universe, such as the formation of black holes and neutron stars, generate vast amounts of positron-electron plasma, a swirling, energetic brew of antimatter and matter. These particles, charged and highly energetic, are ejected at speeds nearing the speed of light, forming powerful energy jets that stretch across unimaginable distances. Every new discovery in this domain acts like a piece of a puzzle, gradually pushing scientists to delve deeper into the nature of antimatter, its role, and its mysterious imbalance in the universe. In 2023, a groundbreaking achievement in the world of particle physics was made by a team of scientists primarily from the University of Oxford. These researchers managed to create the first ever electron-positron beam plasma in a laboratory setting, marking a major milestone in antimatter research. This feat was made possible through a collaboration with the CERN High Radiation to Materials HRMT facility, which played a crucial role in the experiment. What set this achievement apart was the sheer scale of it, producing the highest number of positrons ever recorded in a controlled environment. To achieve this, the scientists employed a powerful proton beam from the superproton synchrotron, SPS. This beam carried an energy of 440 billion electron volts and contained around 300 billion protons. When this beam was directed at a special target composed of carbon and tantalum, an intense reaction occurred, creating a massive particle shower. This shower produced approximately 15 trillion pairs of electrons and their antimatter counterparts, positrons. The resulting beam was so dense that it could sustain plasma oscillations, a hallmark of highly energetic particle interactions. However, this wasn't the first major breakthrough in antimatter research. The discovery of antimatter particles dates back to the mid-20th century. In 1955, two physicists from the University of California, Berkeley, Emilio Segre and Owen Chamberlain, made history by discovering the antiproton, the antimatter counterpart of the proton. Their groundbreaking work earned them the Nobel Prize in Physics in 1959. An antiproton is essentially a mirror image of a proton, but with one crucial difference: it carries an opposite electric charge. It consists of two up antiquarks and one down antiquark, whereas a regular proton is made of two up quarks and one down quark. Just 1 year after this discovery, in 1956, Bruce Cork and his team at the Bevatron, a particle accelerator at the Lawrence Berkeley National Laboratory, identified the antineutron. The discovery of the antineutron marked another milestone in the quest to understand antimatter. But scientists did not stop there. They pressed forward, creating even more complex antimatter particles, including entire antinuclei formed from antiprotons and antineutrons. Despite the success of these experiments, the extreme energy levels involved made it impossible to form full antimatter atoms, where positrons would replace electrons. In 1965, a group of researchers led by Antonino Zik at CERN took yet another leap forward by producing antium nuclei, which are composed of an antiproton and an antineutron. Around the same time, another team at Brookhaven National Laboratory in the United States observed antideuterium, further confirming the existence of these exotic particles. Decades later, in 1995, CERN made an astonishing announcement. They had successfully created the first ever atoms of antihydrogen, the antimatter counterpart of hydrogen. This remarkable achievement was the result of the PS210 experiment, developed by scientists Walter Ouellette and Mario MRE. Following this achievement, Fermilab confirmed the results by producing around 100 antihydrogen atoms. These atoms were incredibly energetic, posing a challenge for detailed study. To address this issue, two major research collaborations, Athena and ATRAP, were established in the late 1990s with the goal of slowing down and trapping antihydrogen atoms so they could be analyzed in greater detail. In 1999, CERN launched the antiproton decelerator, a cutting-edge device designed to reduce the speed of antiprotons from speeds of 2 billion electron volts down to just over 5 million electron volts. Still fast, but a significant improvement. By 2002, scientists working with the Athena project made history again by creating the world's first cold antihydrogen atoms. To accomplish this, they captured millions of antiprotons, cooling them by passing them through a thin sheet of foil before trapping them in a device called a Penning-Malmberg trap. The process, however, was highly inefficient, trapping only around 25,000 of the 25 million antiprotons they began with. Once inside the trap, the antiprotons were still too energetic to cool further. In a brilliant move, the team mixed them with a plasma of electrons, which cooled the antiprotons through collisions. After this cooling process, the electrons were removed using electric fields, leaving behind extremely cold antiprotons. The next step in the process was to combine these cooled antiprotons with positrons from a radioactive sodium source. When the particles combined, some formed antihydrogen atoms, but because these atoms were neutral, they couldn't be confined using electric fields. Instead, they collided with the walls of the trap and annihilated. Despite these setbacks, by 2005, scientists had refined their methods and were able to produce hundreds of millions of antihydrogen atoms. That same year, the Athena project concluded, and many of its researchers joined a new initiative called the Alpha Collaboration, based at CERN. The Alpha Collaboration's main objective was to test CPT symmetry, a fundamental principle in physics that suggests that matter and antimatter should behave in precisely the same way. However, studying antihydrogen posed significant challenges due to its neutrality. Unlike charged particles, these atoms couldn't be held using electric fields, so researchers had to turn to magnetic traps. Specifically, they used a type of magnetic trap known as the minimum B trap, which relies on the fact that neutral antihydrogen atoms have a tiny magnetic moment. This allowed the researchers to hold on to the atoms long enough to study them. In November 2010, the Alpha team achieved a historic milestone by successfully trapping 38 antihydrogen atoms for about 1/6 of a second. Then, on April 26, 2011, the Alpha collaboration stunned the world with another breakthrough. They successfully captured and held on to 309 antihydrogen atoms, some of which remained trapped for as long as 1,000 seconds, approximately 17 minutes. This achievement set a new record, opening up exciting new possibilities for studying the fundamental properties of antimatter. Since that moment, the Alpha collaboration has continued to use these trapped antihydrogen atoms to investigate the spectral characteristics of antimatter, a crucial step in understanding how antimatter behaves under various conditions. Fast forward to 2016, when scientists developed a revolutionary machine known as ELENA, Extra Low Energy Antiproton Decelerator. This device was designed to slow down and cool antiprotons to a level that would allow for precise studies. ELENA operates by first accelerating antiprotons and then controlling their movement in a specialized chamber. This improvement means that over 100 antiprotons can be captured every second. Despite these advancements, creating even a small amount of antimatter remains a monumental challenge. To put it in perspective, it would take several thousand years to produce just 1 nanogram of antimatter, highlighting the immense difficulty involved in its mass production. Currently, CERN, when running at full capacity, can produce around 10 million antiprotons per minute. Even if every one of these antiprotons were converted into antihydrogen atoms, it would take an astounding 100 billion years to create just 1 gram of antimatter, nearly 8 times longer than the age of the universe itself. Furthermore, CERN produces only about 1% of the antimatter generated by Fermilab, and neither facility was specifically designed for large-scale antimatter production. The quest to understand antimatter continues, with each new discovery revealing more about the cosmic forces at play in the universe. But as we inch closer to unlocking the secrets of antimatter, one thing remains clear: the challenge is far from over, and the story of antimatter is still being written. In the ever-evolving world of physics, there are few subjects as enigmatic, complex, and potentially transformative as antimatter. The notion of antimatter has long captured the imagination of scientists, engineers, and even science fiction enthusiasts. However, the reality of working with antimatter is far more challenging and awe-inspiring than most people could ever imagine. According to physicist Gerald Jackson, current technology has progressed to the point where it is possible to produce and capture as much as 20 G of antimatter per year. While this achievement marks significant progress, it's accompanied by one glaring hurdle: the cost. The expenses involved in antimatter production are nothing short of astronomical. Just maintaining a single facility dedicated to the production of antimatter can cost a staggering $670 million annually, making antimatter the most expensive substance on Earth by a wide margin. The journey of antimatter discovery dates back several decades, with some of its most remarkable milestones emerging during the 1970s in the Soviet Union. It was there, in the depths of high-energy experiments, that scientists at the Institute for High-Energy Physics first detected the nuclei of antihydrogen, specifically antihydrogen-3, antihelium-3. In the years that followed, researchers were able to artificially produce these antihydrogen nuclei by colliding atomic nuclei at near-light speeds, an intense process that allowed particles such as antiprotons and antineutrons to combine into antihydrogen nuclei. Fast forward to 2011, and another landmark achievement occurred at Brookhaven National Laboratory, where the STAR experiment team successfully created antihydrogen-4, also known as anti-alpha particles. Meanwhile, aboard the International Space Station, the Alpha Magnetic Spectrometer, AMS, has, as of 2021, recorded at least 8 potential detections of antihydrogen-3. If confirmed, these findings could open up new avenues of understanding regarding antimatter and its role in the broader cosmos. The implications of these discoveries are profound and could lead to a paradigm shift in our understanding of antimatter's place in the universe. However, amid the scientific breakthroughs, one of the greatest challenges continues to be the issue of storage. Antimatter is notoriously unstable. Upon contact with ordinary matter, it annihilates instantly, releasing vast amounts of energy. This creates an urgent need for specialized containment techniques, as antimatter cannot simply be stored in traditional containers. To tackle this problem, scientists have developed devices such as the Penning trap, which uses magnetic and electric fields to hold charged antimatter particles suspended in a vacuum. While this approach works for charged antimatter particles such as antiprotons, it fails for neutral antimatter. For neutral antimatter, a different approach is required: an atomic trap. In 2011, CERN, the European Organization for Nuclear Research, set a remarkable record by successfully preserving antihydrogen for approximately 17 minutes, an achievement that stunned the scientific community. However, the longest sustained containment of antimatter particles remains an achievement by the TRAP experiment, which held antiprotons in a Penning trap for an astonishing 405 days. In 2018, researchers proposed an innovative solution: a portable antimatter containment device capable of holding 1 billion antiprotons. This device would potentially revolutionize the way antimatter is studied, allowing for easier transportation to different laboratories and opening up new frontiers in scientific experimentation. Producing antimatter is not just difficult, it is extraordinarily expensive. As far back as 2006, physicist Gerald Smith estimated that creating just 10 milligrams of positrons, anti-electrons, would cost around $250 million, a figure that translates to $25 billion per gram. For comparison, a 1999 NASA report suggested that producing a single gram of antihydrogen could cost a jaw-dropping $62.5 trillion, an amount so large that it is almost incomprehensible. These astronomical costs are primarily due to 2 factors. First, the particle accelerators used to produce antimatter are highly inefficient, with only a tiny fraction of the required antiprotons actually being produced. Second, these accelerators are in high demand for other scientific research, further limiting antimatter production capabilities. So far, CERN estimates that humanity has produced only a tiny fraction of antimatter, roughly 1 billionth of a gram. This minuscule amount of antimatter is not enough to power even the smallest light bulb, let alone any significant scientific or practical application. To put this into perspective, consider the Manhattan Project, the massive effort that led to the development of the first atomic bomb. Adjusting for inflation, the project cost around $23 billion in 2007 dollars. It would have been far cheaper to develop multiple nuclear bombs than to produce even a tiny fraction of antimatter. Given the extreme costs involved in antimatter production, some scientists have begun exploring the possibility of harvesting antimatter from natural sources. NASA-funded research is currently investigating whether it might be possible to gather antimatter trapped in Earth's Van Allen radiation belts or even in the vicinity of massive gas giants like Jupiter. If this method proves successful, it could drastically lower the cost of acquiring antimatter for both scientific research and potential practical applications, bringing this elusive material closer to our reach. While antimatter research is still in its early stages, there are already some exciting practical applications for the technology. Perhaps the most well-known is in the field of medicine, where positron emission tomography (PET) scans rely on antimatter to create detailed images of the human body. In this process, unstable atoms emit positrons, which interact with electrons to produce gamma rays. These gamma rays are then used to detect diseases such as cancer. In laboratory settings, scientists have also explored the possibility of using antiprotons in a cutting-edge cancer treatment that is similar to proton therapy, where antimatter would be used to precisely target and destroy malignant cells. Beyond medicine, one of the most thrilling prospects is using antimatter as a power source for interplanetary and interstellar travel. Scientists have long speculated that antimatter could be used to trigger nuclear explosions, propelling spacecraft to speeds far greater than those achievable by conventional rockets. The reason for this is simple. Antimatter contains more energy per unit of mass than any known fuel. In theory, antimatter could allow humanity to travel to distant planets or even other star systems with a level of efficiency unimaginable with current technology. The sheer potential of antimatter propulsion is staggering. If we could perfectly harness the energy released during matter-antimatter annihilation, the results would be extraordinary. Just 1 kilogram of antimatter colliding with 1 kilogram of regular matter would release an explosion equivalent to 43 megatons of TNT, almost as powerful as the largest hydrogen bomb ever detonated. However, the challenges of harnessing this immense energy are just as enormous. When positrons and electrons annihilate, they release pure gamma rays, which are notoriously difficult to control. Similarly, when protons and antiprotons collide, they produce a mix of energetic particles, many of which could potentially be used to generate thrust using magnetic fields. Despite the challenges, scientists continue to explore the possibility of antimatter propulsion. The potential for revolutionizing space travel remains tantalizing, but the path to turning this possibility into reality is still a long one. When charged pions, a type of subatomic particle, break down, they produce two primary types of particles. About 22% of their energy is carried away by neutrinos, nearly invisible particles that barely interact with anything. The remaining 78% is transferred into unstable particles called charged muons, which in turn decay into a mix of electrons, positrons, and more neutrinos. If we tally up all the neutrino energy from the process, we find that a staggering 74% of the energy from the charged pions is ultimately carried away by neutrinos, rendering much of the energy in the system difficult to capture or utilize. In another fascinating area of research, scientists have speculated that antimatter could be used to trigger nuclear explosions. Theoretically, if antimatter were to come into contact with regular matter, it would release an enormous amount of energy almost instantaneously. However, the reality is that antimatter is incredibly difficult to produce, and even if we could generate it, storing it in significant quantities remains a near impossible challenge. At present, there is no indication that producing antimatter in large enough quantities for such applications will ever be feasible. During the Cold War, the U.S. Air Force funded research into antimatter, not only exploring its potential use in nuclear weapons, but also investigating whether it could serve as a direct energy source for explosive devices. While those efforts did not bear fruit, The intrigue surrounding antimatter has not waned. As our technological capabilities continue to evolve, it is likely that antimatter will remain one of the most exciting and mysterious frontiers in modern physics. On a broader scale, antimatter research intersects with other groundbreaking areas of physics, including string theory. String theory, a complex and highly speculative framework in theoretical physics, suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings move through space and interact with one another, and their vibrations determine the properties of the particles we observe, such as mass and charge. If string theory is correct, one of its most profound implications is that it might provide an explanation for quantum gravity, a theory that seeks to reconcile the strange, powerful rules of quantum mechanics with the force of gravity. String theory has already had a profound impact on our understanding of the universe, helping physicists make progress in areas such as black hole research, the study of the early universe, and the forces that govern the behavior of atoms. More exciting still is the possibility that string theory could one day offer a theory of everything, a single unified framework capable of explaining all the fundamental forces of nature, from gravity and electromagnetism to the nuclear forces that bind atoms together. Whether string theory holds the key to this ultimate understanding of the universe remains to be seen, but one thing is certain: the study of antimatter, string theory, and the forces that shape our universe will continue to push the boundaries of scientific knowledge for generations to come. However, even after decades of intense research, scientists are still grappling with a fundamental question. Does string theory truly describe the real universe, or does it propose such an abundance of possibilities that it becomes impossible to make definitive predictions? String theory, first introduced in the late 1960s, emerged as an attempt to explain the strong nuclear force, the force that binds atomic nuclei together. At that time, string theory was seen as a promising candidate to unravel the mysteries of fundamental forces. Yet, when another theory, quantum chromodynamics, was discovered to provide a more accurate explanation, string theory was pushed aside. What scientists didn't anticipate, however, was that string theory possessed unexpected properties that could make it a strong contender for explaining gravity at the quantum level. The initial version of string theory, known as bosonic string theory, only accounted for one type of particle, the bosons, which are force carriers like photons in electromagnetism. Over time, the theory expanded, giving birth to what we now call superstring theory. Superstring theory introduced the concept of supersymmetry, a profound idea that suggests a deep connection between two classes of particles, bosons and fermions. Fermions are particles that make up matter, like electrons and quarks. This revelation sparked an entirely new direction in theoretical physics, leading to further developments in string theory. As research progressed, physicists identified 5 distinct versions of superstring theory. But in the mid-1990s, an astonishing breakthrough occurred. All 5 versions were revealed to different perspectives of single unified theory known as M theory. M theory required the existence of a universe with 11 dimensions, not the familiar 3 spatial dimensions and 1 time dimension that we experience in our daily lives. This discovery suggested that string theory could be far more profound than initially imagined, offering a framework that could explain all fundamental forces, including gravity. In the late 1990s, yet another pivotal discovery was made, forever changing our understanding of string theory: the anti-de Sitter conformal field theory, ADS-CFT, correspondence. This relationship linked string theory with quantum field theory, another major pillar of modern physics. Quantum field theory describes particles as excitations in underlying fields, and through the ADS-CFT correspondence, scientists realized that these 2 distinct areas of physics might be able to inform one another, shedding light on some of the universe's most mysterious phenomena. Despite the strides made in string theory, one of its most significant challenges remains: the theory is not yet fully defined. While scientists have made enormous progress, string theory lacks a comprehensive, unified framework that works in all situations. This leaves many questions unresolved. One of the most perplexing issues is that string theory predicts an almost infinite number of possible universes. How do we determine which of these possibilities, if any, matches our own universe? This becomes particularly challenging because string theory's equations require abstract, multidimensional mathematics, which cannot be tested in the traditional experimental sense. For some physicists, this raises a critical concern. Are we investing too much time and energy into an idea that may never be testable? In the 20th century, two monumental theories were developed to explain the universe: Albert Einstein's general theory of relativity and quantum mechanics. General relativity describes gravity and the structure of space and time, especially on large scales like planets, stars, and galaxies. Quantum mechanics, on the other hand, explains the behavior of subatomic particles like electrons and photons. By the late 1970s, these two theories were sufficient to explain nearly everything we observe in the universe, from the smallest particles to the large-scale structure of the cosmos. However, despite their remarkable success, these theories cannot be reconciled with one another. The crux of the problem lies in the fact that general relativity is grounded in classical physics, while quantum mechanics operates on completely different principles. For a true understanding of the universe, scientists have long sought a quantum theory of gravity, a theory that can seamlessly unite the two. This is where string theory comes in. String theory offers a fascinating potential solution. It begins with the idea that the fundamental particles, which we traditionally think of as point-like objects, might actually be tiny, one-dimensional strings that vibrate in space. Instead of treating particles as mathematical points with no size, string theory imagines them as minuscule threads that wiggle and vibrate in space. These strings can be either open, like a short line, or closed, forming a loop. The pattern of their vibrations determines the properties of the particle, such as mass, charge, and how it interacts with other particles. To the naked eye, these vibrating strings would appear just like any other particle, seamlessly fitting into existing models of physics. However, when examined at incredibly small scales, smaller than anything we can currently measure, they could potentially offer solutions to some of the universe's most perplexing mysteries. One of the most exciting possibilities string theory presents is that one of the vibrational patterns may correspond to the graviton, the hypothetical particle that is thought to carry the force of gravity. If this is true, it would mean that string theory naturally incorporates gravity, something that no other major theory of physics has successfully achieved. In the years that followed, researchers working on string theory made another groundbreaking discovery. Different versions of the theory that had once seemed separate were, in fact, mathematically connected through a concept known as dualities. These dualities revealed that what appeared to be one version of the theory from a particular perspective might actually be another version when viewed differently. This led to the realization that all consistent versions of string theory could, in principle, be unified into a single framework, known as M-theory. Yet the precise nature of M-theory remains elusive, and much work still lies ahead before it can be fully understood. String theory has also provided surprising insights into the nature of black holes and gravity. For decades, physicists struggled with paradoxes that arose when trying to apply quantum mechanics to black holes. But in the late 1990s, the ADS-CFT correspondence provided a way to study black holes through the lens of string theory. This breakthrough allowed scientists to explore black holes in ways they never could before, shedding new light on the fundamental structure of space and time. Beyond black holes, the ADS-CFT correspondence has even found applications in fields outside of gravity, such as nuclear physics and condensed matter physics, where it helps explain the behavior of particles under extreme conditions. String theory's ultimate promise is that it could provide a unified theory of everything, an explanation that incorporates all of nature's fundamental forces, including gravity. Many physicists believe that if string theory can be fully developed, it will answer some of the universe's most profound questions. These include why particles have the masses and charges they do, how dark matter fits into the picture, and even how the early universe expanded. If string theory is the key to understanding these mysteries, it could revolutionize our knowledge of the cosmos. but there are still significant hurdles to overcome. One of the biggest challenges is the theory's reliance on perturbation theory, a mathematical technique that approximates the behavior of strings. While perturbation theory has proven useful in many cases, it does not provide a complete picture of string theory, especially when it comes to understanding the theory's full structure without making approximations. Additionally, another unresolved question is how string theory determines the vacuum state, the most fundamental state of the universe. Without this knowledge, scientists are unable to fully grasp how string theory might shape the universe we observe. Some critics argue that string theory, with its unanswered questions, is too speculative. However, many physicists believe that exploring string theory is still worthwhile, as it could lead to profound insights into the nature of reality itself. To better understand where string theory fits into the larger framework of modern physics, it's helpful to examine the foundation of particle physics, quantum field theory. Quantum field theory treats elementary particles as excitations in underlying fields, offering a powerful mathematical framework to describe particle interactions. It uses a technique called perturbation theory to calculate the probabilities of these interactions. Feynman diagrams invented by physicist Richard Feynman are used to visualize these interactions. String theory builds upon this framework, but introduces a radical shift. Instead of imagining particles as points, string theory imagines them as tiny strings that vibrate in space. A key distinction is that in traditional quantum field theory, a Feynman diagram represents a particle's motion as a one-dimensional line, whereas in string theory, this line is replaced by a two-dimensional surface representing the path of a vibrating string. This shift in perspective leads to new mathematics and offers the potential to solve problems that quantum field theory struggles with, particularly gravity. Yet, the challenge remains that string theory lacks a full, complete definition beyond perturbation theory. Without this complete understanding, physicists are limited in their ability to explore the many questions string theory promises to answer. One of the most intriguing aspects of string theory is the scale at which it operates. The length of a fundamental string is believed to be around 1/10,000,000th of a trillionth of a meter, a length so small that it is beyond our current ability to measure. This is known as the Planck length, and at this scale, quantum gravity becomes significant. Here, string theory could hold the key to explaining how gravity operates at the smallest, most fundamental scales. Initially, string theory was developed as bosonic string theory, focusing only on bosons, the particles that carry forces. However, the theory quickly expanded, giving rise to the more comprehensive superstring theory. The journey from a theory of force carriers to a potential theory of everything has taken scientists on a remarkable path, one that is still ongoing. And while the ultimate answers remain elusive, the potential of string theory to explain the universe's deepest mysteries continues to drive exploration and discovery in modern physics. At the heart of modern theoretical physics, the question of the universe's fundamental structure remains a topic of intense exploration. While early theories proposed the idea of point-like particles that make up the universe, it quickly became clear that such models were insufficient to explain the complexity of nature at its most fundamental level. Thus, physicists turned to string theory, a revolutionary concept that proposes that the basic building blocks of matter are not point-like particles, but rather tiny, vibrating strings. These strings are capable of taking on different vibrational modes, each corresponding to a different particle in the universe. However, this initial framework came with significant limitations and issues that needed resolution. One of the most prominent shortcomings was the inability to incorporate all known particles and forces, including gravity, into a unified theory. This is where superstring theory emerged as a more refined model. It expanded the scope of string theory by introducing the concept of supersymmetry, an elegant mathematical structure suggesting that every force-carrying boson, particles like photons and gravitons, has a corresponding matter particle called a fermion, and vice versa. This symmetry not only bridged the gap between matter and forces, but it also opened the door to new ways of understanding the universe. Superstring theory, as proposed, encompasses 5 distinct versions. type 1, type 2a, type 2b, and two variants of heterotic string theory. Each of these models describes different types of strings, each with unique characteristics and implications for the behavior of the universe. For example, in type 1 string theory, there are both open strings, those with loose ends, and closed strings, which form loops. Other versions, such as type 2a and type 2b, focus exclusively on closed strings. These distinctions allow each version of string theory to predict different physical properties, especially when energy scales are varied, and they provide rich avenues for understanding the universe at its most microscopic levels. To frame the universe, we are accustomed to the concept of three spatial dimensions: height, width, and length. These three dimensions provide a foundation for understanding the size and shape of objects in the world around us. But what if this understanding is incomplete? Albert Einstein's groundbreaking theory of general relativity transformed the way we perceive space and time. Instead of treating time and space as separate entities, Einstein proposed that they are intrinsically linked, forming a single four-dimensional entity called space-time. This fusion of space and time is not simply a theoretical abstraction, but a real physical fabric that bends and curves in response to the presence of massive objects like stars and planets. In this framework, gravity is no longer considered a force that acts over a distance, as Isaac Newton had proposed. Instead, gravity is seen as the result of the curvature of space-time itself. Massive objects, like the Earth or the Sun, cause space-time to curve, and this curvature dictates the motion of objects within that space. While this model works exceptionally well for explaining the gravitational interactions between large celestial bodies, it does not account for all the forces in the universe. As physicists continued to push the boundaries of understanding, they began to wonder if there could be more dimensions beyond the four that we experience. Some theories propose that extra dimensions may exist, hidden from our perception, but influencing the fundamental forces of nature in subtle ways. For instance, string theory suggests that the universe operates with additional spatial dimensions that we do not directly observe. These extra dimensions are necessary for the mathematical consistency of string theory, which posits that the universe's fundamental particles are not point-like, but are actually tiny vibrating strings. To make string theory work mathematically, these strings require extra dimensions to move through. Different versions of string theory propose different numbers of dimensions, with some suggesting 26 dimensions, while others predict 10 or even 11 in the case of M theory. But why don't we notice these additional dimensions? The answer may lie in a concept called compactification. This idea suggests that the extra dimensions are not large and extended like the three we experience daily. Instead, they are compacted, curled up so tightly that they are effectively invisible to us. A helpful analogy is to imagine a garden hose. From a distance, it appears to be a one-dimensional line, but upon closer inspection, you realize that it actually has a second dimension, the circular width. An ant crawling along the hose would experience both dimensions, while someone standing far away would not notice the second dimension at all. In a similar way, extra dimensions could be compacted so small that we cannot detect them, even though they may play a crucial role in the functioning of the universe. The specific way in which these extra dimensions are compactified is essential to the success of string theory. They must form particular shapes, and the most well-known of these shapes is the Calabi-Yau manifold. Named after the mathematicians Eugenio Calabi and Xing-Tung Yau, this structure represents a six-dimensional space that is mathematically precise and compatible with string theory. These complex shapes, if they exist, would allow string theory to describe the fundamental forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces. Beyond this, string theory introduces another intriguing concept called brane-world scenarios. In this framework, our entire universe could be a four-dimensional brane, a sort of membrane, floating within a higher dimensional space. Picture a soap bubble in the air. The surface of the bubble represents our universe, while the surrounding space represents additional dimensions that we cannot directly observe. According to this theory, forces like electromagnetism and the strong and weak nuclear forces are confined to our four-dimensional universe. However, gravity, which is much weaker than the other fundamental forces, may have the ability to leak into the higher dimensions, potentially explaining its relative weakness. String theory also includes the idea of duality, a concept that suggests two seemingly different theories may, in fact, be two sides of the same coin. For example, one version of duality called S-duality suggests that a group of particles interacting strongly in one theory can be described as interacting weakly in another theory. This shift in perspective provides new insights into complex physical interactions, showing that they might be simpler than they initially appear. In particular, type 1 string theory has been shown to be mathematically equivalent to another theory known as heterotic string theory, highlighting the deep connections between different string models. Another form of duality, called T-duality, deals with how strings behave when moving through compact extra dimensions. T-duality suggests that if a string moves around a circular dimension of a certain size, it can behave in exactly the same way as a string moving around a much smaller circle. This principle has fascinating implications for the nature of the extra dimensions and their compactification. For instance, type 2a and type 2b string theories, though they appear different at first glance, are actually equivalent when analyzed through the lens of T-duality. The concept of duality extends beyond string theory, with applications in quantum field theory and condensed matter physics. One of the most well-known examples of duality is the ADS-CFT correspondence, which links string theory to quantum field theory. This correspondence has provided deep insights into how particles and forces behave at the quantum level, and has been instrumental in advancing our understanding of the universe's smallest building blocks. Finally, we must discuss the role of branes in string theory. A brane, short for membrane, is a multidimensional object that generalizes the concept of a point particle. A zero-dimensional brane is a point, while a one-dimensional brane is a string. Branes can extend through higher dimensions, and they are crucial to understanding how particles interact. One particular type of brane, known as a D-brane, plays an essential role in string theory. Open strings, strings with loose ends, must attach their endpoints to a D-brane. The behavior of D-branes has led to significant advances in understanding the fundamental nature of particles and forces, including the development of the ADS-CFT correspondence. Thus, through the intricate dance of strings, branes, and higher dimensional spaces, string theory offers a rich and compelling framework for understanding the universe at its deepest level. By unifying all of nature's forces and particles within a single theoretical framework, it provides a tantalizing glimpse into the fundamental workings of reality. Yet much of this remains speculative, and the search for experimental evidence continues as physicists strive to uncover the hidden dimensions that may lie just beyond our perception.